Hey people, welcome to this video. In this video, we will be working on the Mathematics Paper 2 for June 2025, and this is specifically from the Gauteng province. Remember that this paper is worth 150 marks and the time allocated is 3 hours. Okay, moving on to the instructions. Just remember that the diagrams are not necessarily drawn to scale, and if necessary, round off to 2 decimal places unless stated otherwise. And you also have a formula sheet at the back so you can make use of that. Okay, with that being said, let's get into this video. Question 1 says, in the diagram, ADQC and DPB are straight lines. D is a point on the y-axis. A and B are points on the x-axis. The equation of BC is y equals 2x minus 24, and the equation of line AC is 7y minus x is equal to 14. Okay, so this has just not been put in its standard form like the way this one is. And then they tell us that it is given that P is 6 and 1, Q is 7 and 3, T is K and negative 1, and TP is the square root of 293. Okay, so that's the length of that line. And the first question is to calculate the gradient of line PQ. Okay, so we have 2 points on this line. We can find the gradient. Okay, I'm just emphasizing those points. So to find the gradient of a line, the gradient is equal to, and this is the formula, and in place of x1 and x2 with P and Q, you can choose which you would like to be your x1 and x2. So I'm just going to say top minus bottom. So that is y2 minus y1, that's 3 minus 1. So 3 minus 1 all over, and then that's 7 minus 6. So 7 minus 6. Okay, 7 minus 6 is already 1. So 3 minus 1 is 2. So the gradient of line PQ is simply equal to 2. And that is our answer. Moving on to the next question. Question 1.2 says, give a reason why PQ is parallel to BC. Okay, what do we know about parallel lines? If two lines are said to be parallel, okay, if PQ is parallel to BC, then it just means that their gradients are the same because they are sloped or slanted in the same way. Okay, so if we can just show them that the gradient of PQ is actually equal to the gradient of BC, then yes, then they are parallel. Okay, so let's look at BC. We already have PQ, and there we go. The gradient of BC is 2. So we can just show them that. BC's equation looks like this. It says y equals 2x minus 24. So we can see now that the gradient of BC is also equal to 2. Therefore, that means that the gradient of PQ is equal to the gradient of BC. And that is our answer. That is the reason why they are parallel. Moving on to the next question. Question 1.3 says, if Q is the midpoint of DC, calculate the coordinates of C. So, if Q is the midpoint of DC, meaning that DQ would be equal to QC. So we need to find C. Well, we have the midpoint of DC. We have Q, the midpoint of DC, but we also don't have D. We need D so that we can find C. So how do we find D? Look at where it is situated. It is on the y-axis, meaning it is the y-intercept. So in the equation of a straight line, y equals mx plus c. See the c part? That stands for your y-intercept. We actually have the equation of this line AC. It's this, but it's just not in its standard form. Now, you can choose to put it in its standard form, or you could just straight away find the y-intercept. And to find the y-intercept, you simply make x equal to 0. So that's what we'll do. Let's take that equation, 7y minus x equals 14. And let's make x equal to 0. So that's 7y minus 0 equals 14. 7y minus 0 is still 7y equals 14. And if you divide both hand sides by 7, y is finally equal to 2. So we can see what D is now. D is a y-intercept 0 and 2. And this will help us a lot. Okay, so now that we know that this is 0 and 2, to find C, we're just going to use the midpoint formula because this is the actual midpoint and we're going to work through this as if we're trying to find the midpoint, given that we don't know one of the endpoints. So we can call this x and y since it's unknown currently. Okay, so let's just use these points that we have, D, Q, and C. Okay, so to find this midpoint, we're going to say that the midpoint of DC, right, which we know is Q. Now we find that by saying x1 plus x2 over 2, and then y1 plus y2 over 2. And let's substitute. We are substituting these as x1 and x2 because we're trying to find the midpoint of DC, okay? These are the endpoints D and C. Okay, so we can just put it in the order where the x and the y come first. So we can say that that is going to be x plus the other point, the other x value is 0 plus 0 over 2, and then y plus 2 over 2. Now we're saying that this calculation of the midpoint, right? It should give us, if we knew what x and y were, it should give us this midpoint of Q. So we already have that midpoint. We can say that is 7 and 3. And so these are equal. This is the calculation. This is the actual midpoint. So because they're equal, we can equate their x values and say that this means that x plus 0 over 2 is actually equal to 7, that x value, and y plus 2 over 2 is actually equal to 3. Okay, so let's solve now. X plus 0 is still x. And so we just have a 2. So you can just multiply both hand sides by 2, or you can see this as cross multiplying. 7 times 2 is 14, and x times this invisible 1 here is x. So x is equal to 14. Let's just do the same thing over here. And so we're going to just multiply. So that is y plus 2. Okay, when it multiplies to the 1, and then 2 times 3 is 6. So y is just equal to 6 minus 2 when we transpose the 2. So that is 4. Okay, so we know finally that this means that C, that point over there, is simply 14 and 4. And that is our answer. Okay, moving on to the next question. And then question 1.4 says, calculate the size of angle ACB. Let's see what that looks like. So ACB is this angle over here, ACB. How do we find that? Well, do you see that it's created using lines with equations that we have, okay, or at least the gradients. We will specifically use their gradients. So what we can do with this is, let's go ahead and extend these lines. If you extend AC, so we can better understand it, and then we extend BC, then do you see what it creates? There's the angle they're referring to, ACB. Okay, it's this angle because they're vertically opposite. So they're the exact same size. And now to calculate the size of this angle, what we can do is draw an imaginary x-axis. So this is a line that will be parallel to the x-axis. And we're just going to draw it right at that vertex. Okay, at that point where C is really created, that angle over there. Okay, and then from this, you can see that in order to find this angle that we're looking for, we simply have to say, find the angle of inclination of this line BC. And if you take that and you subtract it by the angle of inclination of this line AC, then you're going to get this angle ACB. Okay, so it's this entire angle minus this entire angle. And so that leaves you with that red part. Okay, so let's go ahead and find these. So we just need their gradients to find those angle of inclination. Okay, so let's just go ahead and find them first, those angles, using their gradients. So the gradient of BC is 2. We can find that. And let's just quickly find the gradient of AC. So we'll note down that the gradient of BC is equal to 2. And looking at the equation of AC, let's just get that gradient. Okay, so we can just put it in standard form. In its standard form is y equals mx plus c, meaning y needs to just be on its own. Okay, so let's leave it on the left-hand side. So this is going to be, transpose the negative x, it becomes positive, and we have plus 14 still. And if we divide both hand sides by 7, we'll have 1 over 7x, and 14 divided by 7 is 2. Okay, so this is the equation of AC, and that's what it looks like. Since we know that the gradient of AC is 1 over 7. Okay, now we just need to remember what that equation should look like. We are saying the angle of inclination, okay, of BC, since it creates the bigger angle, minus the angle of inclination of AC. And we will find that. Okay, to find the angle of inclination of BC, we'll say tan theta is equal to the gradient of BC, which we can see is 2. And so to find that angle, the angle of inclination of BC, we're going to use the inverse of tan on both hand sides. You can also see this as transposing tan, so it becomes its inverse. So arctan 2, and on your calculator, you're just going to say shift tan of 2, and it gives that. Now, I don't want to round off yet, just because I would just like to make it as accurate as possible. So I'll leave it as 4349 and just ... so we know we didn't round off yet. And then let's just find the other angle of inclination. So tan theta equals, the gradient of AC is 1 over 7. So we'll say theta of AC is equal to arctan of 1 over 7. And so we're going to finally find that and say this is arctan 1 over 7, just to show that we actually are finding these. So this is 8.1301, and we'll just keep going. Okay, and now finally, let's find those angles. So the angle they're referring to, ACB, to find this, we simply say the angle of inclination of BC, 63.4349, it keeps going, minus 8.1301, and let's find that. So on your calculator, you can simply just go to that end and say shift tan and get that angle of inclination. So put 2 there and just say minus that. Okay, and our answer is finally 55 point, and you see that's going to round down. So it's going to be 0.30 degrees, and that is the size of ACB. Moving on to the next question. Question 1.5 says, calculate the area of quadrilateral BODC. Okay, so let's look at that quadrilateral and just see how we can find the area. So, is this quad BODC? As you can see, it's not any recognizable shape. It's not really a trapezium. No, it can't be a trapezium, because if it was a trapezium, you should have 2 sides being parallel. And we don't have that. Okay, it's not parallel to this at all. Okay, because this is a vertical line and this is not. It's a diagonal line. So it's not a trapezium, meaning we would have to divide it. But let's take advantage of the fact that we actually have other shapes here. So let's divide it using the shapes that we already have here. See how we have this triangle, DOB. We could find the area of that triangle and then find the area of this triangle. And that would work out because you see how they told us to find the angle ACB, right? So we already have this. So to find the area of this triangle, we can simply just use the area rule. Okay, we have an angle. We would be able to find this side since we know what C is now, and we would also be able to find this side. And so that would complete it. And then to find the area of this part, we can see that DO is perpendicular to OB. And so we just need to find B. So we can see the height clearly is 2, and then just find that base by finding B. Okay, so that's one way. Let's explore other ways that we could have also found this. We could also find the area of this shape using other bigger shapes that we have. So look at what we have here. We just need to find DOBC, right? This shape. We could find the entire area of this bigger triangle, and the reason why is it's an obtuse, well, it looks like it is an obtuse triangle that we have here, and we could just use a half base times height to find this one. Yeah, we have this angle, that is true, but we don't actually have to go through the stress of finding this side and this side, because we can actually find this triangle's height. You see, the highest point that this triangle reaches is C. So we could just find out exactly what that height is if we knew what the y value of C was. And there we go, would know the height. So we could find the area of this bigger triangle. Of course, you'd have to find the base, meaning you need to know what A and B are. And then we could also just say, take that entire area and subtract it by the area of this triangle, ADO. Okay, if we subtract it by that, you see how we'll be left with this part. ODCB. Okay, so that's another way. And now just comparing them, they both have things that we just have to find, but this method of finding the area of this entire triangle seems easier because all we need for this is we need A, we need B, and then that's about it. Because if you have A and B, you can just find that distance. It's a horizontal distance, so you don't even need the distance formula. Okay, so let's go ahead and go with that. Okay, so this is our strategy that we're going to use here. We're finding the area of triangle, and this is triangle, let's call it ABC, triangle ABC. And if you subtract that by the area of triangle, this triangle over here, ADO or AOD, so ADO, then we will find this. Okay, so let's just keep this in mind, and now that's what we're trying to do. Okay, so we need to find out what B and A are. So they are the x-intercepts of line BC and AC. So let's find A first, the x-intercept. To find the x-intercept, just make y equal to 0. Okay, so this is our equation, and we'll just say 0 minus x, and then is equal to 14. We're just making that equal to 0. And so you see this will be negative x. So if you just divided or multiplied both hand sides by negative 1, therefore x will just be equal to negative 14. So that is A. A is the x-intercept, negative 14 and 0. And then we need to find the other point B. And that one lies on BC. So to find B, we're just saying it's the x-intercept of this line. So because it's the x-intercept, you make y equal to 0. Okay, so we're saying 0 is equal to 2x minus 24. And then if you transpose negative 24, you're going to get positive 24 equals 2x, which is the same thing as 2x equals 24. And if you divide both hand sides by 2, x is finally equal to 12. So it means that B is that x-intercept 12 and 0. And so to find BC, the base of that bigger triangle, ABC, we're just going to add their lengths. Okay, so from O to A and then O to B, or we could just say the higher one minus the lower one, and then that would just find the length. Okay, so finding BC, we'll finally tell them that BC is found by saying, we'll say the x value of B, 12, minus the x value of A, which is negative 14. So you see how that becomes 12 plus 14, which is finally equal to 26 units. Okay, so we have BC now, and now we just need its perpendicular height, so the area of ABC. So the base is 26. What is the height? This point C, we already found that point, and C was 14 and 4. So since we know that this is 14 and 4, what that means about that height is if this is a y value of 4, then it means that you just went 4 units down, and that's how high this triangle is. It is 4 units. So that's what we're going to take as the perpendicular height. Okay, so we know the perpendicular height of triangle ABC, that is 4 units. Okay, we have everything for triangle ABC. Let's look at triangle ADO now. So with ADO, we actually have the height in this case, because you see that DO is perpendicular to AO because they are on the x and y axis. So that is the height. The height is 2 for DO. And we already found A. So we know that this from O to A, okay, this is negative 14. So it means that AO is 14 units. Okay, so this way is actually quicker than the other way. So we can find that. Okay, so we know in triangle ADO that the base is equal to 14 units, and the height, the perpendicular height, that is 2 units. Okay, here we already know the base and the height. So let's go. We're saying the area of triangle ABC, let's just put it as a whole. To find the area of this quadrilateral, they're referring to BODC. BODC, we simply just say that this is equal to the area of triangle ABC minus the area of triangle ADO. And we're just going to fill in. So to find the area of triangle ABC, we say a half times that base of BC, which is 26 units, times the perpendicular height, which is 4 units, minus a half times the base of ADO, which was 14 units, and times the perpendicular height, which was 2 units. And this will give us the area of quadrilateral BODC. Okay, so we can say a half times 26, that's 13. 13 times 4 is 52. And then minus a half times 14 is 7. And 7 times 2 is 14. So minus 14 again. Okay, and then 52 minus 14. And that gives us 38. So there we go. That's the area of this shape. BODC, it's 38 units squared. Okay, 38 units squared. And that is our final answer. Moving on to the next question. Question 1.6 says, if TP is equal to the square root of 293, which they told us, determine the value of K. Okay, this is not a problem. And the reason why is because it's just K alone that is missing. And they're telling us that we need to find this if the length of this line is 293. So the length of TP. So we're going to take T and P. And because they're telling us the length, we're going to use the distance formula and substitute these values, okay? We can take that as x1 and that's x2 and y1 and y2. And then we'll just substitute that we know what the length of this line is. Okay, let's go. Okay, so to find the distance formula looks like this. And we're saying TP is equal to, and it's the square root of x2 minus x1. So that's k minus 6. K minus 6. I'll just keep that as x2 because I want the k to be in front. All squared plus, and then y2 minus y1. So you have to be consistent. If you start with this, okay, then with the y's, you need to start with this as well. So that's negative 1 minus 1 all squared. And we know what TP is. It is the square root of 293. So we'll say in place of TP, the square root of 293 is equal to, and let's just see what can be simplified here under this radical. So k minus 6 all squared. Let's distribute that. You can't just write this as k minus 6 times k minus 6 and then FOIL out, but that can take quite long. So what we can just do is square the first term, that gives us k squared, square the last term, that gives us positive 36, and then say first term times second term, that will give us negative 6k, and then you just multiply that by 2. So that's negative 12k. Okay, negative 1 minus 1 is negative 2, and then we have that being squared, so that becomes positive 4. And now at this point, you see that what will be a problem would be these square roots. So we're going to cancel them out by squaring both hand sides of this equation. And we have 293 equals, and those cancel. Now we have k squared minus 12k, and 36 plus 4 is 40. Okay, let's transpose this, 293. So 0 equals k squared minus 12k. And then if you say 40 minus 293, that gives us negative 253. Okay, so this is what we have. And we have to factorize. So 253, not a very nice number to use, but not a problem. We're going to open up two brackets, equate it to 0. I was saying k multiplied by k gives us k squared. And we need factors of 253, but one needs to be negative, one needs to be positive, and they should give us a 12 in the middle. Now, with this, it ends with 3, so it's an odd number. It may not have a lot of factors. Here's how you can just quickly do this. 253 is equal to, and when you press the equal to button, press shift and fact so you can see its factors. And so you see that that's 11 and 23. So if it's 11 and 23, but they need to give you a negative 12 in the middle, which should be negative so that we can achieve that. You should make this negative, the bigger factor. Okay, so if you say negative 23 plus 11, you do indeed get negative 12. Okay, so we can see that those are our factors. So plus 11 minus 23. Okay, so therefore, this means that k is either equal to negative 11 or k is equal to positive 23. And now we can decide based on where k is. You see that k is a point that is in the third quadrant. Okay, and in the third quadrant, we know that the x value is negative. The x values are negative here. So we're going to take the negative value. Okay, we'll just tell them that k is actually equal to negative 11. And that is our answer. Moving on to the next question. Okay, question 1.7 says, E, which is A and B, is a point in the second quadrant such that ABCE is a parallelogram. Determine the values of A and B. Let's look at ABCE that they are referring to. Okay, so they're talking about this shape A, B, C, E. Okay, and E is in the second quadrant. So it forms this parallelogram. I should put it like that. And this over here is E. Okay, and that's A and B. So how would we find this given that this shape is a parallelogram? Okay, here's what we can do. Yes, we know that with a parallelogram, the opposite sides are parallel, but that's not really going to help us very well here since we have 2 points missing. So one of the easiest way to deal with this type of question is if you know that this shape is a parallelogram, then you can use this property about parallelograms. You see, with a parallelogram, the diagonals will always bisect each other. And what that means is if this line AC is bisecting this diagonal BE or EB, then it means that the midpoint of AC is exactly the same as the midpoint of BE. So they share a midpoint. So here's how we can find that. We can just go ahead and find that common midpoint. Now, I can't really say it's at D. I don't know where it is. But we're just going to find that midpoint of AC first and then use that midpoint to find E. Just like we did with that first question over here. Okay, we had this point and then we use that midpoint to find that point C. Okay, so let's go ahead and do this. Okay, so all we just need is that point A, which is negative 14 and 0. C is 14 and 4. B, we already found B. B was 12 and 0. Okay, and then E is missing. Okay, so it's going to just look like this. So the midpoint of AC, we'll find that by saying x1 plus x2. So we can just say negative 14 plus 14 over 2. And then y1 plus y2, 0 plus 4 over 2. And so that midpoint of AC is simply just, that's going to be 0 over 2, which is 0. And 4 over 2 is 2. So 0 and 2. Okay, it's that y-intercept. And now because the shape is a parallelogram, then we know that the midpoint of AC is exactly the same as the midpoint of BE. Okay, so we know that 0 and 2 is exactly the same as, and we're just going to find the midpoint of BE. So the x value is A, so we're saying A plus this x value of 12, x1 plus x2 over 2, and then B plus 0 over 2. So this means that we're saying 0 and 2, okay, they're exactly the same, and that's A plus 12 over 2, and that's just B over 2. So we don't really have to write this. We can just start finding it at this point. So we're saying 0 is equal to A plus 12 over 2, and this simplifies to B over 2. So that's just 2 equals B over 2. Okay. Now you see if we cross multiply here, this is a 0, like 0 over 1, right? So if we cross multiply, this stays A plus 12. And then 0 times 2 is still 0. So if you transpose the 12, A is equal to negative 12. And here, just multiply both hand sides by 2 to get rid of this. So times 2 times 2, that's just 4. So B is equal to 4. And those are the values of A and B. A is negative 12, while B is 4. And those are our answers. Moving on to the last question for question 1.8. Okay, question 1.8 says, determine the equation of the line which is perpendicular to AC and then passes through this point. Okay, so to find the equation of this line, we simply need a gradient and then the value of C. We can find the value of C by using this point that we have, Q, 7 and 3. And to find the gradient, they told us that it is perpendicular to AC. So what was the gradient of AC that we had? AC is this line, and here is the equation. We got the gradient at some points when expanding it so that we could just find that y-intercept. Let me just see where that was. Okay, so yeah, we already found that gradient. Okay, so it is 1 over 7. So if that's 1 over 7, then the line perpendicular to AC, the gradient would be, the gradient of that line would simply just be, we'll take that gradient of AC, right, 1 over 7, and you just switch the numerator and denominator, making that 7 over 1, which is just 7, and then you multiply this by -1. So that's -7. And so that will hold the theory that if you have the gradients of perpendicular lines and you multiply them, they will give you -1. Okay, so here's the gradient, and that's a point on the line. So we can either use y equals mx plus c to find this, or y minus y1 equals the gradient, and then times x minus x1. Okay, so y minus, now x1 and y1, that's x1, that's y1, since it lies on this particular line, which is perpendicular to AC. And we're saying y minus 3 equals, and we have -7 times x, and the x value is 7. Okay, so just distribute. So that is -7x. That becomes positive 49. And then we transpose the negative to become positive. So what is 49 plus 3? And we're going to have 52. So this is simply just y equals, let me just put that there, y equals -7x plus 52. And that is the equation of the line perpendicular to AC. And that is it for question 1, which is a total of 25 marks. Question 2, 2.1 says, in the figure below, line 2x minus y plus 1 is equal to 0 is a tangent to the circle with the center M at G. Okay. The center of the circle lies on the line x plus y is equal to 9. Okay, and that's all the information they give us. And the first question is to find the gradient of GM. So looking at GM, do you see how we don't have M? We don't have the coordinates of M, but we do have the equation of the tangent to the circle at G. And what do we know about the tangent to a circle and the radius? Okay, at that point of contact, they are perpendicular. So we can use the properties of perpendicular lines in this case. Okay, so using the gradient of this line, okay, this line, the tangent, we're going to have to find that gradient by making y the subject. So let's rewrite that equation. So make y the subject, and you can just transpose the y. So it's positive y really. So y equals 2x plus 1. So this is the equation of that line. Therefore, the gradient of that tangent is equal to 2. So what does this mean about the gradient of the radius? To find the gradient of the radius, GM, we're simply just going to switch the numerator and denominator. You see with this 2, it actually has a denominator of 1. So we're going to swap the numerator and denominator, so it becomes 1 over 2, and then you multiply this gradient by -1. So it's finally equal to -1 over 2. And that is our answer. Moving on to the next question. The next question, 2.1.2, says determine the equation of GM in the form of y equals mx plus c. So what is the equation of GM? Well, we have the gradient of GM and we have a point on GM. So we can find the equation of this line. So let's go ahead and use y minus y1 equals our gradient times x minus x1. And the points we're using is this point 2 and 5. So we're saying y minus 5 equals our gradient of GM, -1 over 2 times x minus 2. Okay, since that x value is 2. And just simplify. So let's distribute here, and that's -1 over 2x. And that's positive. You see the 2 and the 2 in the numerator and denominator cancel, and they become 1. And then we transpose the -5 and it becomes +5. So y is simply equal to -1 over 2x plus 6. And that is our answer. Moving on to the next question. The next question says calculate the coordinates of M. Okay, so M is that center of the circle. How do we find M? Well, look at where it is. It is a point that is at the center, yes, but we don't really have other points at the circumference except for this. So this is not enough. Okay, so we can just use that. We can see that this line, which we have the equation of, okay, and GM, they intersect at M. Okay, so that would be M, the point of intersection, and also the center of the circle. So let's go ahead and equate those equations. We'll take in x plus y equals 9, and we're taking the equation we just found, which is this. Okay, but let's just put this in its standard form. So y equals, that gets transposed and becomes negative x, and we have plus 9. And now we're just going to equate it with this equation. So we're saying equate these two equations, meaning negative x plus 9 is equal to negative 1 over 2x plus 6. Okay, it's the same thing as saying y equals y. And let's find this. So I'm going to go ahead and take that over just so that the bigger value can also just become positive. So that is positive x minus 1 over 2x. And we have 9 minus 6. So 1x minus a half x is a half x. And this is equal to 3. And then finally x is equal to, when we divide both hand sides by a half or multiply by 2, okay, or 2 over 1, that's just going to be equal to 6. Okay, x is equal to 6. So we found the x value. And now to find the y value, simply substitute this x value into any of these equations. Okay, so to find this y value, we can just use this equation that we already have here. Okay, we equated these two equations, but it's fine to just use that. So we have negative 6 plus 9. 9 minus 6 is 3. So that is our value. And so therefore, it means that M, that center of the circle, is 6 and 3. And that is our answer. Moving on to the next question. Question 2.1.4 says, hence or otherwise calculate the length of the radius of the circle. So we have the center of the circle now as 6 and 3. And now we can finally just use this to find the distance of GM. Okay, so we just need M and G. So let's go ahead and do that. Okay, so using the distance formula, mg or gm is equal to the square root of x2 minus x1. So we can just say top minus bottom. That's 6 minus 2 all squared plus 3 minus 5 all squared. And so gm is equal to, and we're saying 6 minus 2 is 4. 4 squared is 16. 3 minus 5 is negative 2. Squared is 4. And so that is the square root of 20. Okay, and you can either leave your answer like this or round off to 2 decimal places. So we can just say, what is the square root of 20? And that is 4.47, rounded up to 2 decimal places, rounded down, okay, because that's not going to round up. And that is our answer. So that is the length of GM. But of course, if we're like using the equation of the circle, we'll just use the simplified third form. Okay, so if you say the square root of 20, that's simply just going to be equal to 2 square root 5, okay, because 4 times 5 is 20. So we'll just use it like that. Okay, question 2.1.5 says write down the equation of the circle in the form of, and they want us in this form. So it's just the equation of the circle, right? To find the equation of a circle, you need the center and you need the value of r so that you can find r squared. Okay, so we know the center already from the previous question, that is m. Okay, we already know that this is 6 and 3. And r squared, well, we know what r is. GM, the length of the radius, is square root of 20 units, okay, or 2 square root 5. So it means that r squared would be that squared. So that is 20. So you see how this just simplifies everything. And now we can finally just put down the equation of a circle in standard form, which looks like this. So that is x minus a all squared plus y minus b all squared equals r squared. And so the center of the circle, that's what's going to go in place of a and b. And so we're going to say this is x minus, and so that's the first, and so that's the x value, 6 all squared plus y minus 3 all squared. And we know that r squared is 20, so it's equal to 20. And this is the equation of our circle. But of course, they want us to distribute and simplify it and ensure that the right-hand side is equal to 0. So let's go ahead and distribute. We're going to say the first term squared, so that's x squared. Then the last term squared is positive 36. And then first term times second term is negative 6x times 2 is negative 12x. Again, same thing. First term squared is y squared. Last term squared is positive 9. And then first term times second term is negative 3y times 2 is negative 6y. And then we can just go ahead and transpose this 20. So bring it over to the left-hand side and it's minus 20 is equal to 0. And rewrite it in this format. Okay, so we're saying x squared and then plus y squared, then minus 12x minus 6y, and then our constants together. That's 36 plus 9, which we have now, which is 45, and then minus 20, which is 25. So positive 25 is equal to 0. And that is our answer. That is the equation of the circle in the format that they asked for. Moving on to the next question. Okay, question 2.2, and this is the last question for question 2. And it says, determine the equation of the inverse of the tangent to the circle, and this is the circle they're referring to, and they tell us that this tangent happens at 7 and 2. And we need to give our answer in this form, y equals mx plus c. So we're trying to essentially find the equation of the inverse of a tangent. So to find that, we need to first find the equation of that particular tangent to this circle. So in a nutshell, this is what's going on. We have a circle and it's centered at wherever it's centered. This is the equation of that circle. We can actually find the center. And it's an interesting question because this is something that you would actually deal with when practicing. Like, it's a textbook kind of info that you would gain. You would find out that you can have the circle, okay, the circle's equation in two ways. And we can see that from the previous question. You can be given the equation of a circle like this. And then in this way, it helps you to easily see the centers, okay? Or you could be given the equation of the circle like this. Now, with this one, for you to get it back to this format, because that's really what we're doing. They gave us the equation in this form. We need to find that center. So we need it in this form. To do that, you need to complete the square on that format. Okay, so let's see how this is going to work. We need to find the equation of the tangent. So this center is somewhere here. We'll find out what exactly that is. And then the tangent happens at 7 and 2. Okay, so let's just say we have 7 and 2. And 7 and 2 is here. If this is where the tangent happens, it just means that we have a line, okay, touching that point. Okay, so it's only going to touch once. And to find the equation of that tangent, you see that because we would have the center and that point at the circumference, we would actually be able to find the gradient of the radius first. And then we will use that gradient to find the gradient of the tangent, since the radius and the tangent are perpendicular at their point of contact. So the main goal is find the equation of the tangent. Let's go ahead and do that. So we need that center. So we're going to take this circle's equation that they gave us. This is x squared plus y squared minus 26x plus 12y plus 105 is equal to 0. And let's go ahead and put this in this format so that we can easily see the center of the circle. So to put it in this format, we have to complete the square on this equation. Okay, so I just made space because to complete the square, we need some space. Here's what we're going to do. We're going to rewrite this equation, but ensuring that everything with x is next to each other and everything with y is next to each other, and then we will transpose whatever is a constant. So rewrite this as x squared minus 26x plus y squared, and then plus 12y is equal to negative 105. Okay, so now that we have this, we're going to just complete the square. So to complete the square, you're looking at each of these, okay, with the variable x here. So we're looking at this and we're going to get the coefficient of x, okay. So we're going to say x squared minus 26x plus, and we're taking the coefficient of x and you're going to divide that by 2. So negative 26 divided by 2 is negative 13. So we're saying plus negative 13, and then that coefficient of x divided by 2, you're going to square that. So square. And then, let me just leave this in blue. Now we're going to do the exact same thing to this side, okay, with the y's. So we'll say, okay, it still continues as y squared plus 12y, and then plus, now the coefficient of y is positive 12. You're going to take that and divide it by 2 to get 6. And now we're going to take 6 and we're going to square that. Okay, and then it's still equal to negative 105. But here's the thing about equations. If you just did this, you would tamper with this equation and you're just going to completely change it. We're not changing the equation, we're simply changing the way it looks. So what you do on the one side, you must do on the other side. Because we added by negative 13 all squared, on this side, you must do the same on the right-hand side. And so likewise with this, we must also add here by 6 all squared as well. And now our equation is balanced and we can simplify. So with this part, you will notice that if you factorize this trinomial over here, of course, if you got that value, then it's going to simplify to 2 factors that would look like this. Focus on the values that have a squared on it, which is these two. You're going to grab the x and the negative 13, and you're going to say that is squared. Okay, if you had to simplify that and you factorized it, you would get x minus 13 times x minus 13. And so it simplifies to x minus 13 squared. Okay, this is completing the square. And then plus, we're going to grab y down, and then we take what is here. You see, it's a positive 6 here, so we're taking it as positive 6. That's why this one stayed negative 13, because this was negative. So always remember to take the sign in front of it as well. And then we square that, and then it's equal to, and you can just use a calculator for that to just get that quickly. And you see that gives us 100. Okay, so that part is done. And now that this is in this standard form of a circle, we can clearly see that our center has the coordinates 13 and negative 6. And now that we have the center, we can finally find the gradient of the radius, and then that will help us to find the gradient of the tangent. So with this question, it's not really a difficult question. It's just something that you have to remember. You have to remember how to complete the square, and then everything else would work out fine. So that's 13 and negative 6. Okay, and let's go ahead and find the gradient of the radius. So we say to find the gradient of the radius, we say y2 minus y1. So let's just say 2 minus negative 6, which becomes a plus, okay, because it's going to multiply in. So 2 plus 6 over, and if you said 2 minus negative 6, you must say 7 minus 13. Okay, and let's just find out what that is quickly. Okay, so that's going to be 8 and then negative 6. So they're both divisible by 2, meaning that just becomes negative 4 over 3. That's the gradient of the radius. Okay, so now that we know the gradient of the radius, we can finally find the gradient of the tangent. So it means that the gradient of the tangent is simply equal to, let me just put it on this side, it's fine. Gradient of tangent is equal to, you're going to switch the numerator and denominator because we're saying that they are perpendicular. The radius is perpendicular to the tangent at the point of contact. So switch the numerator and denominator. It's now negative 3 over 4. And then you multiply that value by negative 1. So it's positive 3 over 4. That's the gradient of the tangent. Remember, we're just trying to find the equation of the inverse of the tangent. So we first have to find the equation of the tangent, then the inverse. So we have the gradient of the tangent. We have a point on the tangent, 7 and 2. And we can find its equation now. So we can use y minus y1 equals the gradient times x minus x1. And so we're saying y minus, and the y1, that y value is 2, that we're substituting, is equal to our gradient of 3 over 4 times x minus 7. Okay, the equation of this tangent is, we'll say distribute, that's 3 over 4x, and that's negative 21 over 4, and that becomes a positive 2. Okay, so what is negative 21 over 4 and then plus 2? That is negative 13 over 4. Okay, so we'll just put that down, minus 13 over 4. And this is the equation of our tangent. Just keep that in mind. This is the equation of the tangent. Now the question is to find the equation of the inverse of your tangent. So this is the equation of the tangent. To find the inverse, simply take this equation and we're going to switch x and y first. So in place of y, we'll say this is x is equal to 3 over 4, and in place of x, we say this is y, and then minus 13 over 4. So this means now we can finally make y the subject of this equation. So this is x plus 13 over 4 is equal to 3 over 4y. And now we can finally just make y the subject. You see, this is 3 over 4 that is multiplied to the y. So to get rid of it, you can divide both hand sides by 3 over 4, or we could just multiply both hand sides by 4 over 3. See, that will cancel and that will cancel diagonally. So times 4 over 3. And so the equation of the inverse of that tangent is simply 4 over 3x. And then 4 over 3 times 13 over 4. The 4's cancel. So it's plus 13 over 3. And that is our answer. And that is the final question for question 2. So that is it for question 2. Question 3.1 says tan beta is equal to 3 over 4, where beta is an element of 180 degrees to 270 degrees is given. With the aid of a sketch and without the use of a calculator, calculate sine beta. Okay, so we have a trig diagram. Let's go ahead and draw our diagram first. They told us that tan beta is equal to 3 over 4. 3 over 4 is a positive number, so it means that tan is positive in this specific quadrant. And we know that tan is positive in the first and in the third quadrant, in tan's quadrant. But we are also told that beta is an element of 180 degrees to 270 degrees. Okay, so measuring from here, that's 0, 90 degrees, 180 degrees, 270 degrees, and of course, 360. So if it's going from 180 degrees to 270 degrees, you see which quadrant it is referring to? It's the third and the fourth quadrant. But as you can see, the third quadrant meets both criteria. Okay, so it is between 180 to 270 and tan is positive. So our diagram lies in the third quadrant. Okay, so we'll draw our terminal arm. And remember that this goes up to the x-axis and it is perpendicular to the x-axis. So this is beta. That's how it would be measured. Okay, so since we were told that tan beta is equal to 3 over 4, we know that tan from SOHCAHTOA is opposite over adjacent. Okay, so that means that the opposite side is 3 and the adjacent side is 4. Now focus on where these numbers specifically are on the x and y axis. So this 4 is on the negative part of the x-axis. So it's actually a negative 4. But so is 3. 3 is also on the negative part of the y-axis. This is a negative number, so it also takes a negative. And that's why they became 3 over 4, because they were both negative and they're divided to give a positive. So it means that we just have to find the hypotenuse. Okay, so we'll use Pythagoras. We're looking for the longest side. So that is r, our radius. R squared is equal to the shortest side, one of the shortest side squared, plus the other shortest side squared. Okay, so r squared is equal to, that will be 9, and that's 16. 9 plus 16 is 25. And if we square root both hand sides, we can ignore the negative solution since we're finding r, which is a distance, so it will not be negative. Okay, so that means that r is equal to 5 units. And now that we know that r is 5 units, we can finally find sine beta. So it means that sine beta is equal to, from SOHCAHTOA, sine is the opposite over the hypotenuse. So the opposite side, okay, there's beta, opposite is negative 3 over the hypotenuse of 5. So our answer is negative 3 over 5. And that is it for 3.1.1. Moving on to the next question. The next question, 3.1.2, says we need to find the value of 2 minus sine 2 beta. Okay, so this is 2 minus, and we can expand this using the double angle identity for sine 2 beta, which is, so we have minus, and then it becomes 2 sine beta cos beta. Okay, so this is 2 minus 2 multiplied by sine beta. We just found that that was negative 3 over 5. And what is cos beta? So cos is adjacent over hypotenuse. So that means that is negative 4 over 5. So multiplied by negative 4 over 5. And here's what we get. Okay, so at this point, you can just put this on the calculator. And our final answer is 26 over 25. And that is it for this question. Moving on to the next question. Question 3.1.3 says we have to find the value of cos squared 90 degrees minus beta and the minus 1. Okay, so with this, do you notice we have a cos 90 degrees minus beta? So that is, so we can simplify that using cofunctions. So cos 90 degrees minus beta is equal to sine beta. But then let's not forget that this is squared. So we'll apply that by saying this is squared. And you see that when you square this, it just becomes sine squared beta. So this is sine squared beta minus 1. We know that sine beta is negative 3 over 5. So it's negative 3 over 5 all squared and then minus 1. And you can just put this on the calculator to find your answer. Okay, and our final answer is negative 16 over 25. And that is our answer. Okay, moving on to the next question. Question 3.2 says evaluate, and we have to evaluate this expression, simplify it, and this is for 7 marks. Okay, so with the expression, we'll just use our trig rules where necessary, reductions, cofunctions. Okay, so let's start with this. This is, first of all, let's analyze this expression. Do you notice that in the numerator, remember how terms are always separated by plus or minus signs? So this is negative 1 on its own, and then we have plus. Okay, now these two are being multiplied. So it means that we have 2 terms in the numerator. Let's just keep that in mind. So we have negative 1 first, and then cos 180 degrees minus theta. We know that this is not in cos's quadrant. Okay, so looking at the cos diagram, we can see that 180 degrees minus theta is not in the quadrant where cos is positive. Okay, that's where sine is positive. So that is going to change to, so we see how we have a plus here. It's kind of like plus. It changes to negative cos theta. So it reduces to negative cos theta. But then these are still going to multiply at the end of the day. So this now just becomes a minus cos theta. And then it's still being multiplied to this next value. And we have sine theta minus 90 degrees. So with this, it is still a cofunction. Just the way you simplify it is important. Do not try to just take out a negative from it, because this is not actually how it's simplified. Okay, if you did that for this one, it will probably work, but that's not really why it becomes what it becomes. So here's how we simplify this. Notice that our angle is negative. Okay, if the angle is negative, you'll notice that your angles are usually positive. 180 degrees minus theta, 180 degrees plus theta. The angles are usually positive. So we're going to add 360 degrees to that negative angle. So when you add 360 degrees to 90 degrees, we get 270 degrees. So now we have sine 270 degrees plus theta. Notice that this theta is still positive. And then we can still apply cofunctions with this. But here's how we're going to do it. We're going to split 270 degrees up into 90 degrees and the remaining angle that will be there. So if we do that, you'll notice that 270 minus 90 is 180. So this is actually 180 degrees plus 90 degrees plus theta. And then you can group these two together so they serve as a single angle. So this is the same thing as saying sine 180 degrees plus an angle, okay, plus A. See how this would be reduced to negative sine A since we are using tan's reduction. Okay, that's where tan is positive. In the same way, this would also simplify to, but we're going to look at that A as if it's a 90 degrees plus theta. So this simplifies to negative sine of 90 degrees plus theta. And then we can finally simplify this. So this would simplify to negative. Now, you see, this would just be cos theta. Okay, it's not the one that changes to negative. So this will simplify to negative cos of theta. And that is our answer. Okay, so we just know that it simplifies to negative cos theta. Okay, so we're just going to put down negative cos theta. Okay, it's still multiplying, so just keep that in mind. And then this goes all over, and now we have cos negative theta. When the angle is negative, you can just add 360 degrees to this. If you add 360, it becomes cos 360 degrees minus theta. And you see that if you reduce that, that actually is in cos's quadrant. So that will simply simplify to positive cos theta. Okay, and then we are multiplying by sine 90 degrees plus theta, which simplifies to cos theta using cofunctions, and then multiply by tan squared 540 degrees. So what do you notice about this angle? This is an angle that is greater than 360 degrees. So when an angle is greater than 360 degrees, we simply subtract by 360 degrees. And you see here that if we subtract, we're going to get 180 degrees. So this is actually tan squared 180 degrees plus theta. Okay, so let's go. Okay, we're basically done with the reductions. It's just that tan, but we can see it's in tan's quadrant. So this is now negative 1. And this is a negative cos theta multiplied by negative cos theta, which becomes positive cos squared theta. And this goes all over. These two multiply and become cos squared theta. And then we have this. Okay, so with this part, because it's being squared, regardless of whether it's positive or negative, it will just remain positive. So tan 180 degrees plus theta, that gives us positive tan theta. And then that just gets squared. So it ends up just being tan squared theta. Okay, so looking at the numerator, that looks a lot like this identity. See how sine squared theta is actually equal to 1 minus cos squared theta? Because we know sine squared theta plus cos squared theta equals 1. So here we're just making sine squared theta the subject. Okay, so here the only difference is this is negative, that is positive. This is positive, that is negative. So that means there's actually a common factor of negative 1 here. So if we take out that common factor of negative 1, what are we left with? Negative 1 divided by negative 1 is positive 1. And if you divide, you get negative cos squared theta. And there we go. Now they look alike. So we can replace that with sine squared theta. And in our denominator, we have cos squared theta and tan squared theta. We can change that to its identity, which is sine squared theta over cos squared theta. Okay, this cos squared theta in the denominator that it is in, okay, it is on the numerator when compared to this. So since they are multiplying, whatever is common will cancel diagonally. Okay, so this now cancels with that. And all we're left with on the denominator is sine squared theta. And we know that that is sine squared theta on its own. It's not 1 over sine squared theta because this was in the numerator, okay, in that denominator. So now our numerator becomes, we have negative, and this is now sine squared theta. And this goes all over sine squared theta as well. So this simplifies to negative 1, and that is our answer. Question 3.3 says prove the identity, okay, and this is for 5 marks. So with this question, we can go ahead and use the left-hand side. And the reason why is, you see, we can actually distribute that. This is an identity that we know, okay, so we will be able to get this to look like this. So let's rewrite the left-hand side. We'll say left-hand side is equal to, and rewrite. Okay, so to get it to look like this, you can already see the denominator is cos squared theta. So we're definitely changing that 1 minus sine squared theta to cos squared theta, like we saw in the previous question. Okay, so see how we have that. So when we distribute here, you see that it's squared. So one of the easiest ways to square this, instead of rewriting it twice as sine theta minus cos theta times sine theta and then foiling out, is here's what we can do. It's squared. It's a squared binomial. So we're going to square the first term, and that gives us sine squared theta. And then square the last term, and that gives us positive cos squared theta. Then we'll say first term times second term, which just gives us negative sine theta cos theta. And then we multiply this by 2. So we have negative 2 sine theta cos theta, which already looks familiar. Okay, so this is what we have, but always make sure you are focusing on what the right-hand side looks like so that you know which type of decisions really to make. Okay, so we can go ahead and change that to the cos squared theta. So identity, that is cos squared theta. And now on the numerator, you see how they have a 1, and then they have this 2 tan squared theta. So this has to do with this negative 2, okay, that negative 2 there. So we can just put these together. We know that sine squared theta plus cos squared theta, that's what gives us 1. So that's going to be 1 minus 2 sine theta cos theta. But at this point, okay, I still can't change that, because if you change it to its double angle identity, sine 2 theta, now you have a 2 theta and you have a cos squared theta. That's not going to work out. They won't simplify. So let's leave it like this. We have cos theta, and then this goes over cos squared theta. And let's see how we can simplify this. Just make sure you always look at the right hand side and see, how does this get to look like that? First of all, we have a 1 and we have cos squared theta, and then this. So it means that they separated these. Okay, they took this fraction as a whole and they separated it like this by saying this is actually equal to 1 over cos squared theta minus 2 sine theta cos theta over cos squared theta. Okay, and that's what was done to separate them. So this stays 1 over cos squared theta, and this will simplify to a cos theta, and a cos theta cancels here. So one of it is gone and you just left with 1. Okay, and so we know that sine theta over cos theta give us tan theta. So that's minus 2 tan theta. And there we go. It is equal to the right-hand side. And we have proven the identity. Okay, and that is it for this question, question 3. Question 4.1 says, given cos A minus B equals cos A cos B plus sine A sine B, we need to use the above identity to deduce that sine A plus B is equal to this. Okay, so we are using this identity, using this rule to create the expansion or the identity for this. So the main focus is on sine A plus B. But we need to expand this using the rule above. Okay, so first of all, do you notice that in this rule we have cos, but here we have sine. So we need to change this to cos as well, so it can also just reflect what we have there. So this is equal to, and we're going to change it to cos using cofunctions. So it becomes cos 90 degrees minus this angle. So we're going to treat that as that single angle. Okay. And now that we have this, we can go ahead and just distribute that negative in. So we have cos 90 degrees minus A minus B. And the reason we're doing that is because you see how this says cos A, a single angle, minus B, another angle. So we needed to also say that. But right now it was just saying 90 degrees minus A plus B. Okay, we can't treat A plus B as one single angle to expand this to, because then it's going to include A and B, but we needed to have an A and a B. Okay, so now that we have it in this format, what we can do is, so that it includes a single angle of A and a single angle of B, we're going to group these two together. 90 degrees minus A goes together because when expanding this, 90 degrees minus a can still be simplified to a using cofunctions. Okay, so now looking at this, do you see that it's in the format above? They say cos of an angle minus another angle. And so we can now start expanding. So this is equal to cos of, this is our first angle, 90 degrees minus a. So since theirs expanded to cos of their first angle, we'll also say this expands to cos of our first angle, which is 90 degrees minus a. And then cos of the second angle, and our second angle is also b because we also have a minus. So this becomes cos b, and then the sign changes to a plus. So we'll also go ahead and change that to a plus, and it is sine a, so sine of that first angle. So we'll also just say plus sine a, and our first angle is 90 degrees minus a, and then sine b, so sine of our second angle, which is also b, just like this. Okay, and now all we have to do is simplify further. So we can use cofunctions to simplify this. This will become cos 90 degrees minus a becomes sine a, and then we have cos b plus sine 90 degrees minus a becomes positive cos a and sine b. So there we go. It becomes sine a cos b, cos a sine b, just like this. Okay, so it is finally equal to that, and there we go. We have deduced an identity for sine a plus b. Moving on to the next question. The next question, 4.1.2 says, hence or otherwise determine the general solution of the equation, and this is the equation we have. Okay, so you can see a repetition of 15 degrees and 48 degrees. So they're just using this expansion over here. Okay, so what we can do is just take this over to the right hand side. So we have sine 2x plus 50 degrees, and this is now equal to positive sine 15 degrees cos 48 degrees, and these are positive. But notice how it says sine cos and then sine cos. We can just let it say sine cos cos sine like that previous question. So we'll rewrite the cos 15 degrees first. So it's plus, we have cos 15 degrees and then sine 48 degrees. Okay, so then we're going to simplify that using the compound angles identity for sine. So this is sine 2x plus 50 degrees is equal to, and this becomes sine 15 degrees plus 48 degrees. So this is sine 2x plus 50 degrees is equal to, and this becomes sine, and when we add those together, that is like 45 plus 15 is 60, so that's 63 degrees. Okay, so now we can finally start solving for x. You see that despite the fact that this has sine, it's sine 63 degrees. So it's an actual number. For example, if I said sine 90 degrees, sine 90 degrees is the same thing as sine 1, okay, because we know sine 90 is 1. So we just see this as there is a number here, a value, okay, and it's a positive number because it's sine 63 degrees. If you say sine 63, so we know that this is a positive value. Okay, we'll keep this in mind. So let's go ahead and find our reference angle. So the reference angle is equal to, and we're going to, it's like taking this sine over. So we will have the inverse of sine, so shift sine of sine 63 degrees. Now what you will notice is they would cancel each other out because we have the inverse of sine being applied to the sine function. And so they will cancel and you'll just be left with 63 degrees. Okay, like that. So this is equal to 63 degrees. That is our reference angle. And now we can finally start solving for x. Okay, so this is the angle that we didn't apply the second function of sine to. So this is what we're solving for. We'll put that as our subject. 2x plus 50 degrees is equal to, and here's the thing with these answers. Remember how sine is a positive value? Okay, so for this, you can't just use the reductions where sine is positive. That's in the first and the second quadrant. So using 180 degrees minus theta, and then just taking that as theta. So we're saying 2x plus 50 degrees is equal to, and our reference angle is what is theta. So we'll leave this as 63 degrees. This is our first solution, plus k of 360 degrees. Okay, we'll tell them where k is an element of integers soon. And the second solution will be found here. Again, we'll say 2x plus 50 degrees, that is equal to, and we'll use that reduction where sine is positive. The second solution is 180 degrees minus our reference angle of 63 degrees. Again, plus k of 360 degrees, since the sine graph repeats itself every 360 degrees. Okay, let's solve for x over here. So if we transpose 50 degrees, we have 2x is equal to 63 minus 15 is 13 degrees plus k 360 degrees. And then we can just divide both hand sides of this equation by 2. So if you divide by 2, x is finally equal to 13 divided by 2 is 6.5. So that's 6.5 degrees plus k of, and 360 divided by 2, that is 180 degrees. Okay, so that is our first solution, our first general solution. And then the second one, we're going to have to just find out quickly what 180 minus 63 is. So 80 minus 63, and then that's going to be 17. So we have 2x plus 50 degrees. We'll transpose that, of course. So 2x is equal to, this becomes 117 degrees, okay, because we still have the 100, just saying 80 minus 63. And then if you transpose that 50 degrees, if we subtract by 50 degrees, we'll find out what that is. So plus k, 360 degrees. And then 117 minus 50, that's going to be 67. So we have 2x is equal to 67 degrees plus k, 360 degrees. And now we can divide both hand sides of the equation by 2. Okay, so x is finally equal to 67 divided by 2, that is 60 divided by 2, which is 30, and then 7 divided by 2, which is 3.5. So that is 33.5 degrees plus k of 360 divided by 2 is 180 degrees. Okay, and in both cases, we should tell them, of course, this is where k is an element of integers and where k is an element of integers. And those are our solutions. Moving on to the next question. Question 4.2 says, if cos x plus 30 degrees is equal to negative 2 sine x, deduce that tan x is equal to negative 1 over the square root of 3. Okay, so since we have to deduce that tan x is equal to negative 1 over square root 3, we could have tried to focus on making this equation look like this. But that seems very difficult because we just have x here. Okay, so what we could do is use the equation that they told us here, right? This is what they've given us. They said that this is true, right? That cos x plus 30 degrees is equal to negative 2 sine x. And what we can do here is form tan x and find out exactly what tan x will be. So because it has sine and cos, we are at an advantage and we can actually do this. So we're going to create tan x using this, and naturally it should be equal to negative 1 over the square root of 3. Okay, so we're working with this equation. So what can we do with this equation? Well, we can expand this part using the compound angle formulas. So we'll have cos x, and that will be cos 30 degrees. And the sign will change to minus. So minus sine x sine 30 degrees, which is equal to negative 2 sine x. And the whole point is to create tan x. Okay, so let's go ahead and simplify with these special angles that we have here. So this is cos x multiplied by cos 30 degrees is the square root of 3 over 2. And then minus sine x multiplied by sine 30 is 1 over 2, which is equal to negative 2 sine x. Okay, so these multiply. And so what we'll have here is the square root of 3 over 2 cos x. But this is good because now you see that cos x is on its own and sin x is also on its own. So what we can do here is multiply these two together and then transpose it so that it's also with the other sin x, since they are like terms now. So I'll say this is equal to, when we multiply, they'll become negative 1 over 2 sin x, but then when they go over, they become positive. So it's going to be positive 1 over 2 sin x and then minus 2 sin x. Okay, so this is the square root of 3 over 2 cos x. We're getting closer to making it become tan x. So these are like terms. So what is a half minus 2? That's going to be negative 3 over 2. Okay, you could also just say minus 4 over 2. So negative 3 over 2, and we have sin x. Okay, now at this point, because we have cos and sin, we can form tan. We know that tan x equals sin x over cos x. So sin x needs to stay on the numerator and cos x will be on the denominator. So this needs to stay here, and we can divide both hand sides by cos x so that we can create tan x. Okay, so we divide also by cos x. Now we just want tan x to be alone on one side. So the number also needs to go, meaning this number needs to leave since this is going to become our tan x. So we'll also divide both hand sides by this number, negative 3 over 2. So negative 3 over 2. And now what do we have? So simplifying this, all of this, these two cancel. So that simplifies to tan x. And this is equal to, here the causes cancel, cos x cancels. And what is the square root of 3 over 2 divided by negative 3 over 2? You can use tip and times. So we will swap the numerator and denominator and then change the division to a multiplication. You see here that diagonally 2 and 2 would cancel, and you're just left with the square root of 3 over negative 3. So that is negative root 3 over 3. Okay, so they want us to show them that tan x is actually equal to negative 1 over square root 3. Okay, so do you see that this is the answer you would get if you rationalized the denominator? Here's what I mean. If we have this fraction 1 over square root 2, we could either decide to leave it like this or make the denominator a rational number. So you would do that by multiplying both the numerator and the denominator by that same surd that we have, whatever surd was in the denominator that made the denominator irrational. So here we'd multiply the numerator and the denominator by root 2. Okay, and then that would make it a rational number. So the denominator, when these two multiply, they just become 2. And when the numerators multiply, they become the square root of 2. And there we go. Our denominator is now a rational number. So with this one, the denominator is already a rational number. We have to convert it back to a form where the denominator is an irrational number. Okay, so you see that to convert it from an irrational denominator to a rational, we just multiply it by that surd in the numerator and the denominator. So in this case, it's really doing the same thing, because if you were trying to do the opposite to get it back to this, okay, you would say, okay, just divide by whatever surd we had, which is the square root of 3, right? And so what we would do is say, we could just divide by the square root of 3 over the square root of 3. You can't just divide by the square root of 3. You'll be tampering with the value of tan x. So the reason it's square root 3 over 3 is because we're really just dividing by 1. But we're dividing by 1 in the form of square root 3 over square root 3, because they would divide to give 1. So doing this using tip and times, okay, when we're dividing by a fraction, you tip the numerator and denominator, you swap them, meaning this would stay square root 3 over square root 3, and you change the division to a multiplication. So do you see that in order to put it back to a format when the denominator is irrational, you would still have to multiply the numerator and denominator by the surd that you had. So the square root of 3 over the square root of 3. And so let's see what we get. So tan x is now equal to, and so those multiply and become negative 3 over the denominator is now 3 square root 3. But then in the numerator and denominator we have a 3, so they cancel. And so finally tan x is equal to negative 1 over the square root of 3, because that's what's left in the numerator. And there we go. We have shown them that truly tan x is equal to negative 1 over square root 3. And that is our answer. Question 4.3 says, given the expression, and we have 4 sine x cos x. Okay, so bit of double angles over there. And over 2 sine squared x minus 1. Also double angles, just placed differently. So we have to simplify the above expression to a single trigonometric ratio. Okay, so we have 4 sine x cos x. This can be written as 2 multiplied by 2 sine x cos x. Okay, if we take out a common factor of 2 there. And here, so you see how this looks similar to the identity for cos 2x, okay, that being 1 minus 2 sine squared x. So here, the 1 is negative, but it's positive here. Here, the 2 sine squared x is positive, but here it's negative. So it means there's just a common factor of negative 1. So if we take that out as a common factor, what are we left here with that negative 1? We'll be left with positive 1. And again, that common factor of negative 1 is out. What are we left with here? We'll be left with negative 2 sine squared x. Okay, and then this simplifies to, so we still have the 2 outside there. Now that will become sine 2x over, and we have negative, and now we know, yes, this is the identity for cos 2x. So that simplifies to negative cos 2x. Okay, so we've got sine 2x over cos 2x. They will become tan, okay, 2x. So this is just 2 divided by negative 1, which is negative 2. So our answer is negative 2 tan 2x. And that is the single trig ratio it simplifies to. Okay, moving on to the next question. The next question says, for which value or values of x in the interval where we have x being greater than negative 90 degrees but less than 90 degrees, will the above expression be undefined? Now we know that an expression will be undefined if its denominator is equal to 0. So let's look at our expression. Our expression's denominator is 2 sine squared x minus 1. Okay, and we can just say that is equal to 0. Along the line, we were able to simplify this to negative cos 2x. So regardless of whether you work with this one or this one, you will still get those same values because they are equal to each other. Okay, these two equations are equal. So let's just work with this. Okay, so 2 sine squared x minus 1 equals 0. And we can transpose the 1, and so it will make it positive. And then we can divide both hand sides by 2. So we'll have sine squared x equals 1 over 2. And then we can square root both hand sides. But that will result in a positive and a negative solution. So we'll look at that. So this is now sine x is equal to positive or negative. The square root of 1 is still 1, but the square root of 2 is root 2. Okay, so we have two equations really. We can just solve for x where sine x is equal to positive 1 over square root 2, or where sine x is equal to negative 1 over square root 2. Okay, let's just find that reference angle first so we can just find out where these are. So the reference angle is, you're just going to say shift sine of this value that we have here. So what will that give us? We say shift sine and 1 over root 2, we get 45 degrees. Okay, so we know that the reference angle for both cases, we can just call it 45 degrees. Okay, now because we got a reference angle like 45 degrees, it's really not necessary to go through the whole procedure of solving for general solutions. Also because the interval that we are looking for these answers in, it's not that far, okay? It's not a wide range that we have. It's just from negative 90 to 90 degrees. So here's what we can do. Okay, now because the reference angle is 45 degrees, this actually is going to help us a lot. Here's what we can do with this. Okay, reference angle is 45 degrees. So we could draw a sine graph just to better understand what we're looking for and so that we can avoid finding any unnecessary solutions just because they've given us a small interval, not a wide interval, okay, negative 90 to 90 degrees. So let's just draw our sine graph. The sine graph looks like this, and this is going to repeat itself again 360 degrees before this, okay? So this is what it looks like. So from 0 to 360 degrees, and from 0 to negative 360 degrees. But we're specifically looking for these solutions where x is greater than negative 90 degrees, but less than 360 degrees. So let's just focus on that part. Okay, so to 90 degrees, and then this is negative 90 degrees. Now this y value of 1 over square root 2, it's a value that is very close to 1. So we can look at it like this. 1 over square root 2, the positive one. Okay, this can be y equals 1 over root 2. And so do you see that the places where the sine graph has a y value of 1 over square root 2 would be here and of course here. But we don't want this one because it's out of bounds. It goes beyond our restriction. So we want this one. And then the other one we're trying to find is where y equals negative 1 over root 2. Okay, notice that the absolute value of these are still exactly the same. So y equals negative 1 over root 2. So where does this appear within the bounds that we have? It's just here, okay? So how do we find these values? Well, we know what the reference angle is. So if the reference angle is 45 degrees, with that positive 1 over root 2, that is the first answer we're going to get. It's going to be positive 45 degrees. Now, because of the symmetry of the sine graph, okay, see what the sine graph does over here like that? It'll do the exact same thing over here. So if we went from 0 degrees to 45 degrees to get a y value of 1 over square root 2, then how much degrees to the left did we go from 0 degrees to this value over here so that we can get a y value of negative 1 over square root 2. These graphs, okay, if this is symmetrical, what it does on this side, it does the exact same thing on this side. So it means that it would have only gone 45 degrees to the left, and so this next solution would appear at negative 45 degrees. Okay, if you didn't want to look at it this way, you could go ahead and go through that whole long method of finding out what exactly x is, the general solution for x for both, and then substituting integer values in place of k when we say plus k 360 degrees, just so that you can find the values that are within this interval. But we could have also looked at it from the graph's perspective and looking at how the graph looks. Okay, so we can see here that the values of x for which this expression is going to be undefined is at x equals negative 45 degrees or x equals 45 degrees. Okay, we're not going to take these ones. Yes, I know that it has a y value over here, but it is beyond this negative 90 degrees, so we won't take that. And that is our answer. Moving on to the next question. Okay, question 4.3.3, the last question for question 4, says without using a calculator, determine the value of 4 sine 15 degrees cos 15 over 2 sine squared 15 degrees minus 1. You would notice that this looks very familiar. Okay, if you compare it to the previous question, and let me just pin it and we can compare. Okay, if we compare this to the previous question, okay, do you see that it's following the same form? So in place of x, we can just call that 15 degrees. And so whatever this simplifies to, we're just going to replace that with 15 degrees. Okay, so this simplifies to like this one, negative 2 tan 2x, but our x is 15 degrees. So negative 2 tan 2 multiplied by 15 degrees. And so this is really just equal to negative 2 tan 30 degrees. Okay, so they did say do not use a calculator. So we would have to simplify tan of 30 degrees. So tan 30 degrees using the circle or the triangles, or you could just use the OHA rule. So we can just find this using the OHA rule. So I'll say OHA. So that stands for opposite, hypotenuse, and adjacent. And then the angles we'll put here is 30 degrees, 60 degrees, and 45 degrees. And then our numbers. So we'll start like this: 1, 2, 3, 3, 2, 1, and 1, 2, 1. And then in each row, square root the biggest number. So that's the square root of 3, the square root of 3 here, and the square root of 2. Okay, so what is tan 30 degrees? Remember from soccer, toa, tan is toa, opposite over adjacent. So it's tan 30 degrees. So we go to the 30 degrees row, and we're saying it's the opposite over the adjacent. So that is equal to, we still have negative 2. So we're still multiplying. So it's equal to tan 30 degrees. So it's that 1 over the square root of 3. So that's 1 over root 3. And so from this, our answer will simply just be equal to negative 2 over root 3. And that is our answer. Okay, and that is, of course, if we didn't use a calculator, you could have used the calculator. If you did, it will simply just rewrite this as an expression with a rational denominator. So just multiply numerator and denominator by the squares of 3, and you would have negative 2 root 3 over 3. So that is an alternative. Okay, and that is it for question 4. Question 5 says, in the diagram below, the graph of f of x equals cos x plus m. Okay, clearly they're referring to this one. There's a little bit of a confusion because they put g here and then g there as well. But from what is going on here, we just have cos x and then plus m. Okay, that is a vertical shift. You see how this, the highest it should reach normally is 1, but it's reaching a half. So clearly that's this graph over here. Okay, so f of x equals cos x plus m, and then g of x is equal to sine x plus n. And yes, we can see that this one is the graph that has been shifted horizontally. Okay, so they say that these graphs are drawn on the same set of axes for where x is an element of negative 240 degrees all the way to 240 degrees. A is the x-intercept of f and has coordinates of 60 degrees and 0. And then B is the turning point of G and has coordinates 60 degrees and 1. And the first question is to determine the values of M and N. Okay, so let's go ahead and start off with this graph of F. So this is our graph of F because we see where that is. That is a vertical shift that has been applied to this graph. It has not been shifted horizontally because we can still see, okay, it has a minimum at 180 degrees. It has a maximum at 0 degrees. So it's not been shifted left or right, but it has been shifted down. So what it would have looked like if we shifted it back up is it would have been here with a maximum at 1. And then when you take it from this point and you shift it down to a half, you see that we must have shifted it down by a half unit. So a half units down gets us to this point. And so that would mean that M is actually, because it's moving down, it's negative a half because it has to go down by a half unit. So M equals negative a half. And let's look at what N is. N, looking at the graph of G, okay, so this graph, what happened to this graph to get it to this point? So we have an N applied to the X, meaning this was either shifted to the left or the right. Okay, remember that it is a sine graph. So naturally the sine graph, the Y value of 0, normally on the original sine graph, Y equals sine X, that one would always appear at 0 degrees. So it means that this is what this graph should have looked like, but it was shifted so that it moves from this Y value of 0 being at 0 degrees till that Y value of 0 being at negative, that looks like negative 30 degrees because it looks like we're moving in 30. So negative 30 degrees, negative 60, negative 150, negative 120. Okay, so clearly this graph was shifted from this point and it was shifted 30 degrees to the left. Okay, so when a graph moves to the left, then it's going to be a left movement would be you would add. And then if it moved to the right, you would subtract. So it means that this N value here is actually N equals positive 30 degrees. Okay, if we added 30 degrees there, it would shift that graph 30 degrees to the left. So n is equal to 30 degrees, and that is our answer. Moving on to the next question. The next question is to write down the amplitude of f. So to look for the amplitude, you don't really have to look at the graph because they've already given us the graphs. So looking at the graph of f, the amplitude of f, you would focus on the value in front of cos x. So that value in front of cos x is an invisible one. So it simply means that the amplitude of f is equal to 1. And that is our answer. Okay, that would be the height of this graph from the midline. It just means that if you found the middle of this graph, then from that midline to the highest point, that would be 1. And of course, again, from that midline to the lowest point, that would be 1 unit as well. Okay, so that is our answer. The amplitude is 1. Moving on to the next question. The next question, 5.3, says, if h of x equals g of 2x, write down the period of h. So the period is affected by whatever you put in front of x. Okay, that will control how quickly or slowly it completes a cycle. So the graph of g is this graph, and do you see that it's a sine graph? Now, in front of x currently, we don't really have any number. It's not like it says 2x or anything like that. So it means that this period has not been tampered with. It still holds the original period of the sine graph. So the sine graph naturally has a period of 360 degrees. If you change, so we're saying g of 2x, so in place of x, we're substituting 2x. So it means now that you have a 2 in front of your x. To find the new period, we'll take the original period of that sine graph, which is 360 degrees. It takes a sine graph 360 degrees to complete a single cycle. And so you're going to take that and divide it by the value in front of x. So there will now be a 2 applied to that x, okay, in that sine graph. So divided by 2, and our period is 180 degrees. Moving on to the next question. The next question says, for which values of x will f of x multiplied by g of x be less than or equal to 0? So let's look at the possibilities of the y values of f multiplied by the y values of g, giving us a value that is either negative or equal to 0 within this interval. Okay, so for them to multiply and give a negative value, then f could be positive, and at the same time, or for the same x values, g can be negative, and then it will give us a negative value, a value less than 0. Or it could be a situation where f is negative and g is positive, and then they give us a negative value. Okay, in both cases, we can also consider places where they are actually equal to 0 as well. So let's go ahead and see if we can see any of these on our graph. Okay, so looking at our graph from 0 to 240 degrees. So we're only supposed to look here within 0 to 240 degrees. Where is the graph of f positive? Where does it have positive y values? And at the same time, the graph of g has negative y values. Okay, so I'm just going to cancel these out so it's not confusing. So we have this being f, and that is g. Okay, so with that, you see that g has positive y values over here. Okay, all through here, it has positive y values. So the x-axis is going to be a very important factor to take into account. Now, we'll be looking at the graph of f, but for the same x values. So if we're looking at it for these same x values, moving this line around, do you see that the graph of f also has a positive y value? Okay, they both have positive y values, which is not what we're looking for. We need one to be positive, the other to be negative. As we keep moving, see, g has a positive y value here, while f has a positive y value as well. We'll keep moving, and then we get to this point. G has a y value of 1, while f has a y value of 0. And that is one of the requirements we're looking for. And as we move more to the right, you see that now f has a positive y value, while g has a negative y value. It maps to a negative y value. And so this is going to be valid all through here. So we're going to mark from this point here and until here, and then we'll stop here. Because you see that if you go beyond this, G is no longer positive. Beyond this, G is negative. So we'll go there and let's select here for the same X value. So you need to make sure you're selecting for these same X values. So it will be this part of the graph of f. Okay, so it works here. Here we can see that we have positive y values for f, and at the same time we have negative y values for g all through. And then of course after this, we can see that it's no longer working anymore because the graph of g now goes below the x-axis, and so it has negative y values. And for these same x values, the graph of f also has negative y values all through. So we can see that it only worked between these two values from 60 degrees, okay, that's 30, 60, and then all the way to, that is 120, 150, all the way to 150 degrees. Okay, and these are also included values because we can see here that the graph of f has an actual y value of 0. That is one of the requirements. It can be less than or equal to 0. The products can be less than or equal to 0, and we'll take that. So it means that it's going from 60 degrees to 150 degrees, and those are included values. So it means that x is greater than or equal to 60 degrees, but less than or equal to 150 degrees, because we can see that at 60 degrees and 150 degrees, we also have the product of these y values giving us 0. Okay, so that is it for that question. Moving on to the next question. Question 5.5 says, describe the transformations that the graph of G has to undergo to form the graph of P, where P of x is equal to negative cos x. Okay, so it's a transformation from G to P. So let's see what G looked like again. The graph of G is the sine graph, okay? So n is 30 degrees. So we know that the graph of G is sine x plus 30 degrees. And they're saying that it gets transformed to look like this. P of x equals negative cos x. Okay, so how do we get from this to this? Okay, so in this case, because one is sine and one is cos, we can focus on them both saying the same thing, either saying cos or saying sine. So because we have sine x plus 30 degrees, it'll be easier to change this to sine. So P of x can actually be changed to, we still have negative here, but because we have cos, we're going to have to use cofunctions. Remember how sine 90 degrees minus x is equal to cos x. So in place of cos x, we can simply just say this is sine 90 degrees minus x. Okay, so we have negative sine 90 degrees minus x, and now we can compare them. Looking at the graph of G and the graph of P, how do we get from sine x plus 30 degrees to sine 90 degrees minus x? Okay, now at this point, you see how this minus x may be a little bit of a problem. So here's the thing with cos x. We could either make this equal to sine 90 degrees plus x or sine 90 degrees minus x, because they'll both give us cos x. Okay, the only one that becomes negative is that one that says cos 90 degrees plus x. That becomes negative sine x. Okay, but we're trying to change from cos to sine, not sine to cos. So in this case, instead of leaving it as 90 degrees plus x, because this has a positive x, and so it's not as easy to just translate it like that, we're going to change that to this one, which is, we say sine 90 degrees plus x. Okay, and now we can compare them. So if we have sine x plus 30 degrees and then sine 90 degrees plus x, it's the same thing as rewriting this as negative sine x plus 90 degrees. And now, how did we actually go from this graph to get to this graph? Let's just look at the transformation that took place. So we went from x plus 30 degrees to x plus 90 degrees. If you went from 30 degrees to 90 degrees, what happened? From 30 degrees to 90 degrees, you would have to add 60 degrees. When adding 60 degrees, what kind of transformation is this? And remember, we are adding to the x. Okay, so if we're adding to the x, this is a left or right shift, but we are adding 60 degrees. When you add, we're shifting to the left. So this means that to get from the x plus 30 degrees to the x plus 90 degrees, we first shifted the graph 60 degrees to the left. Okay, but then do you see that here, this is a positive, right, sign, and here this is negative sign. So what that just means is that this y value, right, it had a negative multiplied to it. Because if you say g of x and you say multiply by -1, it becomes negative g of x, meaning whatever g was, it will just become negative. Okay, so if you multiply the y values of a graph by -1, what that means is that this graph was reflected through the x-axis. So if we had a point over here, a and just 1 and 2, if you reflect this through the x-axis, right, so it's going to appear here, see how this point will change to, the x value is still 1, but the y value will now be -2. So if you notice that all the y values of a graph change to negative, then it means that this graph was reflected through the x-axis. Okay, a reflection through the x-axis causes all the y values to change. So they'll just be multiplied by -1. So this graph was shifted 60 degrees to the left and reflected across the x-axis. And that is our answer. And that is it for question 5. Question 6 says, in the diagram below, ABD is in the horizontal plane and BC is a vertical pole. The angle of elevation from A to the top of the pole is equal to x. And then we also told that it's given that angle ADB is equal to 2x and CBD equals 90 degrees and AD is equal to BD. Okay, and we need to prove that AD equals h over 2 sine x tan x. Okay, so the main goal is find an expression for the length of AD. So here's what we can do. To find AD, we're going to have to use this triangle first, since that is the triangle that AD is a part of. And we could just go ahead and use the sine rule. So to use the sine rule here, we need this side because this is what we're looking for. And then we need the angle opposite it. And then we need another complete side. Now this is an isosceles triangle, meaning these two angles will be exactly the same. So we could think about using this side and that angle and then this side and that angle. But the problem is these two are exactly the same. So BD is also AD. Okay. Now at this point, we can just look at what we have here. Notice how we have H. So H comes from this triangle. So somehow this is involved. We have to get that. So the only way to include H in this triangle is if we were using H so that we could find AB. So instead of in this triangle, using this side AD with the angle opposite it, and then using BD with the angle opposite it, we're not going to do that anymore. We're rather going to use AD with that angle, and then this angle with BD. Okay, so using the sine rule. So the main goal is find exactly what this angle is over here, and then find an expression for AB. Okay, so it's an isosceles triangle. Let's go ahead and start with these angles. So this is 2x, meaning the angles in the triangle add up to 180 degrees. And so this angle, let's just call it angle ABD. Angle ABD would be found by saying 180 degrees minus 2x, right? But then remember that these two are exactly the same. Okay, so you can't start by doing that. But the thing is with 2 and 3D trig, it's not Euclid where you need to put reasons. Okay, so we can just tell them that angle ABD is equal to angle BAD. So angle BAD, those because we have an isosceles triangle. And so let's go ahead and find angle ABD. So this is 180 degrees minus 2x, but then there are two of the exact same angle. So to find one of them, just divide that angle that we find by 2. So 180 degrees minus 2x divided by 2. And so this means that angle ABD is simply equal to 90 degrees minus x. Okay, so we found an expression for this. ABD is 90 degrees minus x. And now all we have to find is AB. Okay, and then we'll use the sine rule. So looking for AB. AB can be found using this right angle triangle here. We already have x, and we need to include h. So we're taking the opposite side and we're trying to find AB, which is the adjacent side. So opposite and adjacent means we need to use the function tan. So we'll say tan of the angle there, which is x. Tan x is equal to the opposite side is h over the adjacent side, which is AB. So h over AB. And we're just trying to find out what AB is. So to make AB the subject, you can just multiply both hand sides by AB. And so you'll be left with AB tan x here. And then divide both hand sides by tan x to get AB on its own. So what that would do, it will result in us having AB is equal to h over tan x. Okay, I'm just seeing it as transposing the AB and then it goes to the numerator, transposing the tan x and goes to the denominator. Okay, so this is what we have for AB. And now finally we can use the sine rule here. Since this is h over tan x, using the sine rule, we're simply just saying we're trying to find AD. So we'll say AD over sine of the angle opposite it. So the angle opposite AD is that 90 degrees minus x. So 90 degrees minus x is equal to, and then we're going to say another side that is available, which is AB over sine of the angle opposite it, which is the 2x. So sine 2x. But we already know that AB is h over tan x. So this is h over tan x. And now all we have to do is simplify. So this is AD over, we can use cofunctions here to simplify that. So sine 90 minus x is equal to cos x. And this is equal to, and this is a fraction, h over tan x. And we are dividing by sine 2x. So we can use tip and times here. So if you put this over 1 to make it a fraction, you're going to have to tip it, meaning swap the numerator and denominator, and then change the division to a multiplication. So now we just have AD over cos x is equal to, and these multipliers will become h over tan x sine 2x. Sine 2x can be expanded, so let's just expand it. So it's going to become 2 sine x cos x, okay, using double angles. And finally, to just get AB on its own, we can multiply both hand sides of this equation by this cos x in the denominator. So times cos x. And so finally, AD would be equal to, we have the cos x going to the numerator because it's multiplying to the numerator. It's cos x over 1. So that's h cos x over, and we have tan x times 2 sine x cos x. And cos x cancel on the numerator and denominator. Therefore, AD is finally equal to h over, and this will simplify to 2 sine x tan x, just like they have it. Okay, so that is our answer, and that is the only question we have for question 6. Question 7.1 says, P, Q, R, S, and T lie on the circle with center O. PR is perpendicular to OQ, and these two lines intersect at F. POT is a straight line, and angle P1 is equal to 42 degrees. Okay, so if POT is a straight line, you can see that this is a diameter since it passes the center of the circle. Okay, and question 7.1.1 says, determine given reasons the sizes of the following angles. And they first want us to find the size of angle R1. Okay, let's look at angle R1. Angle R1 is over here. So it's at the circumference, and you notice that angle R1 is being supported by this diameter POT. So it means that the size of it is 90 degrees because it is supported by a diameter. So we can tell them that angle R1 is simply equal to 90 degrees. And this is because we have an angle in a semicircle. Okay, and that is our answer. Moving on to the next question. Next question B says find the size of angle S. So remember that angle R1 is now 90 degrees. To find angle S is at the circumference. Okay, so we need to apply rules about angles at the circumference. But you notice that angle S is supported by RT. Okay, you can say the chord RT. You can also say the major arc RT. Now, we don't really have any other angle that is also being supported by this major arc. So we can't really apply rules about angles in the same segment, or even angle at the center is twice the angle at the circumference. But do you notice that if you go from angle S and you join 4 points on the circumference of the circle, so to R, P, and T, we have a cyclic quad. And what do we know about the opposite angles of a cyclic quad? They add up to 180 degrees. Okay, so it means that angle S will be found by saying 180 degrees minus 42 degrees. So that's how we'll find angle S. We'll say 180 degrees minus 42 degrees. And this is because of opposite angles in a cyclic quad add up to 180 degrees. And this is finally equal to 138 degrees. And that is our answer. Moving on to the next question. The next question C says we need to find the size of angle PQR. Okay, so we know now that angle S is 138 degrees. And now how do we find the size of angle PQR? So this angle over here. Okay, it's also an angle at the circumference, but it's quite big, and again, we can't really see any other angle supported by the same chord or that major arc. So let us join 4 points. Okay, so here we can join till T and then to P. So we have a cyclic quad again. So in order to find angle Q, and you can just check the mark allocation for this. This is 3 marks, okay? So it wouldn't be the same steps, the same one-step process like the previous question. So if we want to find angle PQR, we would have to find angle T2. So let's go ahead and find angle T2 first. Looking at this, angle T2 is actually part of this triangle PRT. And you see that it's the only angle missing in this triangle. So we can find it. We can say 180 degrees minus 90 degrees minus 42 degrees. And that will give us angle T2. So let's find angle T2 first. Angle T2 equals 180 degrees minus 90 degrees minus 42 degrees. And the reason is the sum of angles in a triangle. So therefore, angle T2 is equal to 48 degrees. Okay, now that we know what angle T2 is, how do we find angle PQR? So again, using that cyclic quad, you see that the opposite angles of a cyclic quad add up to 180 degrees. So we can simply say that angle PQR would be found by saying 180 degrees minus 48 degrees. And that is because of the opposite angles of a cyclic quad add up to 180 degrees. So therefore, angle PQR is equal to 132 degrees. And that is our answer. Moving on to the next question. The next question, 7.1.2 says, if PR is 7 centimeters, QR is 4 centimeters, determine the length of QF. Okay, so let's look at this in our diagram. Okay, so looking at our diagram, knowing that we found this to be 132 degrees, they tell us that PR is 7 centimeters. So this over here is 7 centimeters. And then QR is 4 centimeters. And we need to find the length of QF. Okay, so how would we do this? Okay, so do you notice that they're giving us the dimensions that will help us with this right angle triangle we have here? They want us to find QF, but they've given us QR. and they gave us the entire length of PR. So we can simply just find this side RF, and we would be able to find QF. Okay, so to find RF, do you see that we have a line from the center of the circle perpendicular to the chord? And so that line will bisect this chord. So let's go ahead and start off there first. We'll tell them that FR is equal to FP because of the line from the center of the circle perpendicular to the chord. Okay, so since those are equal, it means that if this entire length is 7 centimeters, then each of them are 3.5 centimeters. So we can just say that is going to be 3.5. Okay, so let's just conclude what FR is, because that's what we're trying to find. Therefore, FR equals 3.5 centimeters. And now we have everything to find QF. Okay, so using the theorem of Pythagoras here, you can see that QF is one of the shortest sides. So we'll say QF squared is equal to the longest side, QR squared, minus the other shorter side, FR squared. Okay, and the reason for this is the theorem of Pythagoras. So we can just tell them it's because of Pythagoras. And now we can just find QF. So we'll say that QF squared is equal to, they told us the length of QR. It's 4 centimeters. So that's 4 squared minus FR squared, which is 3.5 squared. Okay, so let's go ahead and just find out exactly what this is. Okay, so at this point, you can just go ahead and square root both hand sides. So on your calculator, you'll find out what the square root of 4 squared minus 3.5 squared is. And that will be the length of QF. Okay, so looking at that, rounding off to 2 decimal places, you see that 6 is going to round that 3 up to a 4. So QF is equal to 1.94 centimeters. And that is our answer. Moving on to the next question. Question 7.2 says, in the diagram, B, D, and C lie on the circle with center O. AB and AD are tangents to the circle at B and D respectively. And we're also told that angle BAD is 59 degrees. Okay, determine, given reasons, the sizes of each of the following angles, and 7.2.1 says we need to find the size of angle B1. Okay, so let's look at where B1 is. So B1 is over here, meaning it's between a tangent and a chord. But the thing about this is we can't really use the tan-chord theorem here because the angle between the tangent and the chord is equal to the angle supported by that same chord. So the angle supported by that chord is angle C, which is empty right now. And we can't really say, okay, we can find angle C by saying these are opposite angles, because that's not a cyclic chord, okay? This is outside the circle. So we could use that we have a triangle here, triangle ABD, okay? So, and it has this angle. Now, when we have tangents drawn from the same point to a circle, those tangents are equal, okay? So it means that line AD is equal to AB. And so this is an isosceles triangle. And so we will be able to find these two angles since we have one of the angles in this triangle. Okay, so let's go ahead and start by telling them that AB is equal to AD. So AB equals AD. And the reason why is because tangents from the same point drawn to a circle are equal. Okay, tangents from the same point are equal. And now we can go ahead and tell them that these two angles are equal. Okay, so angle B1 is equal to angle D1. So we're concluding that angle B1 is equal to angle D1. And the reason they are equal is not just because this is an isosceles triangle, it's because these sides are equal. And so the angles opposite their equal sides are also equal. So we can tell them that. Okay, and so now that we know they are equal, let's go ahead and use the sum of the angles in a triangle, seeing that these two are exactly the same. Okay, so we can go ahead and tell them that angle A, which is 59 degrees, so 59 degrees plus angle B1 plus angle D1 that they add up to 180 degrees because they're the angles in a triangle. Now, we already know that angle B1 and D1 are equal, but we're trying to find angle B1. So in place of angle D1, we're going to replace that with angle B1 since they are equal. So that's angle B1 equals 180 degrees. So now this is 2 angle B1. Okay, it's double that. And then we'll say 180 degrees minus 59 degrees. Okay, so 2 angle B1 is finally equal to, this will be 121 degrees. And then we'll have to divide both hand sides by 2 to finally solve for angle B1. So it means that angle B1 is equal to, and that's going to be 60.5 degrees because 120 divided by 2. Okay, so angle B1 is equal to 60.5 degrees. And you can fold this in your diagram just in case it helps you with the next calculation. Okay, moving on to the next question. Question 7.2.2 says find the size of angle O1. Angle O1 is at the center, okay? So it's at the center. Let's use theorems that have to do with angles at the center. So the angle at the center is twice the size of the angle at the circumference as long as they're supported by the same chord or arc. Now, right now with this angle at the circumference, we don't have anything there. But do you remember that this angle over here, right? This is the angle between a tangent and a chord, so it's equal to the angle supported by that same chord. So over here, this would also be 60.5 degrees. Okay, so let's go ahead and tell them that angle C is equal to angle B1. Okay, so angle C equals angle B1, and this is because of the tan chord theorem. So it means that angle C is also equal to 60.5 degrees. And now that we know angle C, we can go ahead and use that to find angle O1. So angle O1 is double the size of angle C. So it means that this is the larger one. So we can go ahead and say angle O1 is equal to twice the size of angle C. And so this is because of the angle at the center being twice the angle at the circumference, as long as they're supported by the same chord or arc. And so angle O1 is equal to twice of 60.5 degrees. And you see that this takes us back to 121 degrees. And that is our answer. And that is it for question 7. Question 8.1 says, in the diagram below, A, B, and C are points on the circle with center O. And we need to prove the theorem which states that angle AOC is twice the size of angle B. So to prove this theorem, we're just going to make one construction. And we're joining BO, and we can just extend it to a point. So we can say join BO and extend it to, let's say, P. Okay, since P is not really being used here in this diagram. So that's what we're going to do, and make sure that you write down every construction that you have made. Okay, so any description of how that has been constructed will do. And we're going to go ahead and name this angle B1 and angle B2. And this is angle O1 and angle O2. Okay, so let's go ahead and prove this theorem. So with this, do you notice that angle O1 is the exterior angle of this triangle AOB. So it will be equal to the sum of the two opposite interior angles. So we'll start off with that. Tell them that angle O1 is equal to angle A plus angle B1. So angle B1 plus angle A, and this is because of the exterior angle of a triangle. Okay, but you also notice that this is the radius. OA is the radius and OB is also a radius. So it means that they are equal in length. And if they're equal in length, then it means that the angles opposite their equal sides are also equal. So tell them that OA equals OB because these are equal radii. So we can tell them radii. But this would now conclude that angle A is actually equal to angle B1. So it means angle B1 is equal to angle A. And so we can now update this equation. So this will conclude that angle O1 is equal to, and we're going to just use one of these angles instead of saying angle B1 and angle A. You can keep the focus on angle B, okay? Since this is what we're trying to prove, that AOC equals to angle B. So in place of angle A, I'm just going to say angle B1. So it's equal to angle B1 plus angle B1. And so angle O1 is equal to 2 angle B1. And that's what we have so far for this. Okay, also remember that these two angles are equal because of angles opposite equal sides. So we'll also tell them that angles opposite equal sides. And now we can look at the other triangle that has been created because of this line. So that triangle is triangle OBC. Okay, so we have this triangle over here, and this line is an extension of it. So we have an exterior angle as well. So angle O2 is equal to angle B2 plus angle C. Now we can go ahead and tell them that angle O2 equals angle B2 plus angle C. Now the same situation is going on here. Do you see how OC is a radius and OB is also a radius? So OB is equal to OC. Tell them OB equals OC. Also, don't leave the reasons out here. Okay, so the reason for angle O2's equation is because of the exterior angle of a triangle, and OB is equal to OC because these are equal radii. And so because we have two of those sides being equal, we'll have two angles being equal, and that is angle C and angle B2 that are equal. So tell them that angle B2 is equal to angle C, and the reason is because we have angles opposite equal sides, okay, are equal. Okay, and now we can update our equation. So it means that angle O2 is finally equal to angle B2, and again we're going to change that to angle B2, keeping the focus on angle B. So angle O2 is equal to 2 angle B2. Now notice with what they asked us to prove, we have angle AOC, okay, which is this angle over here, AOC. If we add angle O1 and angle O2, they make up angle AOC. So let's go ahead and do that so we can find that. So angle O1 plus angle O2 is equal to, now angle O1's final equation, it was equal to 2 angle B1. So we'll say 2 angle B1 plus angle O2's final equation was 2 angle B2. But here's the thing, angle O1 plus angle O2 make up that angle AOC. So in place of O1 plus O2, we'll say that this is actually angle AOC, and this is equal to, now notice that we have a common factor of 2 here. So we'll take it out as a common factor, and what are we left with? We're left with angle B1 plus angle B2. And now AOC, angle AOC equals twice the size of what is angle B1 plus angle B2. Do you see that if you join these angles together, you get that angle they were referring to in the proof, angle B. So it means that angle AOC is equal to twice angle B, twice the size of angle B. And that is our answer, and that is our proof, and that's how we prove this theorem. Okay, moving on to the next question. Question 8.2 says, in the diagram below, we have BC being parallel to FD, and angle C3 is equal to X. Okay, and then they tell us that AFB and EFC are straight lines, and we need to determine, giving reasons, 4 other angles equal to X. Okay, so X is over here, and they told us that these two lines were parallel. So we can use fun angles and just see if we can find any fun angles that relate to X. Okay, so from this point, when I try to move X from where it is, I'm trying to find out another angle equal to X. I see that because of this, we have corresponding angles like this. But unfortunately, it's at an angle that they haven't even named. So they probably don't even want us to find that. Okay, so I checked the memo and I see that they actually left a note on this particular question in 8.2, the entire 8.2, saying not to mark this, and it's probably because not enough information was given. But from that, it also seems as if they meant that these two lines, AD and CD, are actually tangents. So for the sake of practice, let's take it like that. Okay, let's say these two are tangents, and let's go ahead and find four other angles equal to x. Okay, so if these were tangents, four other angles equal to x. Well, this is convenient for it to be a tangent because of where it is. If this is a tangent and this is a chord, okay, the angle between the tangent and the chord is equal to the angle supported by that same chord. So angle C3x is also equal to angle B. So we can also just put that down. And of course, this is equal to x. So we'll just say it is equal to x. And the reason why is because of the tan chord theorem. Angle between the tangent and the chord is equal to the angle supported by that same chord. Okay, so that's the first one. And now looking at this, since this is angle B, right? Since this is x, then you see that AC is a chord and it is supporting this angle, angle B at the circumference, but it's also supporting the angle E at the circumference. So they would also be equal because of angles in the same segment are equal. Angles in the same segment are equal. Okay, what else is equal to x? Okay, if these are two tangents, right? If this is a tangent and that is a tangent, then we know that tangents drawn from the same point to a circle are equal. So if these two are equal, we have an isosceles triangle. And so, because we have two sides being equal, the angles opposite their equal sides will then be equal as well. To show them this, we would have to start by telling them, because these are tangents, we'll say AD is equal to CD. And this is because we have tangents from the same point. Okay, and now that we show them that those lines are equal, their angles are therefore equal. So angle A3, therefore angle A3 is actually equal to angle C3, and so that is equal to x. And the reason is because we have angles opposite equal sides being equal. Okay, so that is 1, 2, 3 angles that we have proven are equal to x so far. Now, what other angle would be equal to x? Okay, so we've used the tangents. We have used the tan chord theorem. Okay, so that's still using the tangent. And how else? Okay, remember that we were given parallel lines. Okay, so these two lines are parallel. What can we find with that? Okay, so if these two lines are parallel, then we can see it like this. So since these two are parallel, then this forms an F, okay? So it means that this angle over here, angle F2, is equal to angle B, okay? Because of corresponding angles. So we can go ahead and tell them that as well. And this is because of corresponding angles on parallel lines. Okay, you can also just tell them the lines that are parallel. That is, FD is parallel to BC. You can just say BC is parallel to FD. And that is our answer. Okay, those are the four other angles that would be equal to x. So that would just be the case had they told us that these two lines are actually tangents. Okay, moving on to the next question. Okay, the next question, 8.2.2 says, prove that AFCD is a cyclic quadrilateral. Okay, let's look at AFCD. So AFCD. How do we prove that this is a cyclic quadrilateral? Okay, just remember that there are three ways or three theorems that speak about a cyclic quad. So here are the theorems. The first one is this case. If we ever have a quad and we notice that the exterior angle is equal to the opposite interior angle, then this is a cyclic quad. And the second situation is this. If we notice that these two angles in the same segment are equal, then this shape is also a cyclic quad. And lastly, if the sum of the opposite interior angles add up to 180 degrees, then this is a cyclic quad. Now you can see from the way the diagram looks that it's this one that we'll be looking into, okay, just because of these lines intersecting. And straight away, do you see that we have that situation there? Okay, those are the angles in the same segment. These two angles are supported by this chord AD, and they're exactly the same. That is X and that is X. And that's why it's always important to name your angles as you find them. Make sure you note it down that you have found that so that you can just keep track of it. Okay, so we'll just go ahead and tell them that we have angle F2 being equal to angle C3. So angle F2 is equal to angle C3, and that has been proven already. That's something that we can see. So because of that, that would mean that this shape is a cyclic chord. So we'll tell them in conclusion, this means that AFCD is a cyclic chord, and this is because we have equal angles, okay, in the same segment. So the angles in the same segment are equal. Therefore, this is a cyclic chord. Okay, so we can say that we have equal angles in the same segment. It's just describing what we have. Or we could say this is the converse of the angles in the same segment theorem. Okay, and that is it for 8.2. Moving on to 8.3. Question 8.3 says, in the diagram below, AC is a diameter. So AC is the diameter of the circle with the center O. AC is produced to P. And then they tell us that angle B1 plus B2 is equal to 127 degrees. And angle P is 16 degrees. And the first question is to show, given reasons, that BP is a tangent to the circle at B. Okay, so how do we show that this is a tangent to the circle? You would have to use theorems related to tangents. Now, with theorems related to tangents, we know about the theorem which states that if we have a tangent to a circle and a line from the center of the circle, that line is going to be perpendicular to the tangent. Okay, the radius is always perpendicular to the tangent at the point of contact. But the thing is, we don't really have a radius going to that tangent. Yeah, sure, we have OA and OC, but we don't have one going there. So we'll rule that theorem out. The next theorem we can use is the tan chord theorem. So got a tangent going to a circle, and if we notice that the angle between the tangent, okay, and the chord, that chord is equal to the angle supported by that chord, okay, this angle, then that is indeed a tangent. Okay, so in this case, we're looking at it as if BP is not a tangent yet. We're just going to show that it is. So for us to do that, this is our tangent. So the angle between the tangent and the chord, we'll use this chord because if we looked at it on this side, we don't really have an angle here. So there's nothing to work with there. So we can look at it like this. This is BC, and so that's our chord. The angle between the tangent and the chord is equal to the angle supported by that chord BC. So we need to show that angle B2 is actually equal to angle A, which would just mean find angle B2 and then find angle A. And if they are equal, then this BP actually is a tangent. Okay, so let's go ahead and prove this. We're going to have to find angle B2 and angle A. So we are required to prove, or to show at least, that angle B2 is equal to angle A. We'll just hold on to that. Now, looking at angle B2, how can we actually find this angle? Well, we'll have to find angle B1 to be able to understand what angle B2 is, because we know what B1 plus B2 is. That's 127 degrees. So how do we find angle B1? Angle B1 is, do you see how it is supported by a diameter? So it's equal to 90 degrees. Okay, so we can start off there and tell them that angle B1 is equal to 90 degrees because we have an angle in a semicircle. Okay, so that's our first step. And now that we found angle B1, okay, this is 90 degrees, we can find angle B2. So angle B1, 90 degrees, plus angle B2 give us the 127 degrees, okay, B1 plus B2. So to find angle B2, we'll simply say 127 degrees minus 90 degrees. Okay, and the reason for this is because this was already given. They told us about B1 plus B2. Okay, so angle B2 is equal to 37 degrees. Okay, so angle B2 is 37 degrees. And now that we know this is 37 degrees, all we have to do is find angle A. And if that's equal to 37 degrees, then BP is a tangent. How do we find angle A? Well, angle A is part of this big triangle. And you see how this triangle has two available angles already? Okay, so that is 16 degrees and 127 degrees, okay, B1 and B2. So to find angle A, we'll simply say that angle A is equal to 180 degrees minus 127 degrees minus 16 degrees. And the reason for this is because we have the sum of angles in a triangle. Okay, and 180 minus 127 minus 16 indeed is equal to 37 degrees. So there we go. Because angle B2 is equal to angle A, then this means that the tan chord theorem is true here, making BP a tangent to the circle at B. So we can now finally conclude, because these two are equal, therefore BP is a tangent to the circle at B. Okay, and the reason for this would be not because of the tan chord theorem. The tan chord theorem is used when you already know that this line is a tangent. But because we were trying to prove that it was a tangent, we're going to say this is the converse of the tan chord theorem. Okay, and that is our answer, and that is it for question 8. Question 9.1 says, in the diagram below, PQ is equal to QR, which is equal to RS. And we're also told that VR is parallel to TS. Okay, the first question, 9.1.1 says, determine the value of TV over VP. Okay, so since these three sides are equal, we could just call them A. Okay, so if that was A, and that was A, and that was A, because they're exactly the same, how would we find TV over VP? So using the proportionality theorem, because we have a line parallel to one side of the triangle, what we can do here is we're just going to pair it with the side that it is in proportion with. So that's going to be RS over PR. And you see how PR is made of two sets of A's added together. Okay, so here's what we can tell them. We can tell them that TV over VP is equal to, and so that's going to pair with RS, or we can say SR over RP. So SR over RP. And the reason for this is because we have a line drawn parallel to one side of the triangle, or we could also say proportionality theorem. Okay, so that is what we have. And so therefore, TV over VP is equal to, now you see how that's A, and then that adds up to 2A. If you said A over 2A, what does that simplify to? It's going to simplify to, when the A's cancel, it's just going to be 1 over 2. So that's exactly what this is equal to. Its ratio is 1 over 2. And that is our answer, and that is our reason. And moving on to 9.1.2. So question 9.1.2 says, determine the value of the area of triangle PQV over triangle PST. Okay, so let's go ahead and highlight those triangles. Okay, so looking at the triangles that they asked for, also just remember that we were able to show them that TV over VP was equal to 1 over 2. So looking at those ratios, TV takes the 1 part. You can call that another letter. You can call it B. And then VP takes 2 parts. So we can call that 2B. Okay, so we're only going to use their ratios. We don't really care about the letter for now. We'll just use their ratios. It's really just to differentiate between a length and a ratio. Okay, so since they say PQV over PST, PQV is this triangle over here, PQV. Okay, so that triangle. And then PST is the bigger triangle, as we can see, PST. Okay, so how will we find their areas over each other? Well, we definitely cannot use a half times the base times the height because we don't have a perpendicular height in both triangles. However, we can use the area rule. And with the area rule, you're going to have one single angle. And it would work if both triangles have that common angle. And we can see that in this case, that is angle P. So in order to find these areas, okay, the ratio that they give us, we will say a half multiplied by the side. Okay, so we're looking at this triangle on the top. That is this one over here. And we're going to say a half multiplied by PV multiplied by PQ and then times sine of angle P. Okay, so a half multiplied by PV, we can just start by telling them that times PQ times, or you can just say sine of angle P, and this goes over a half multiplied by, and now we're going to use the sides of this bigger triangle. So that will be a half multiplied by PT multiplied by PS, and then sine of their center angle, that center angle. So we'll say a half multiplied by PT multiplied by PS, and then sine of angle P. And so here's the thing about it. Because angle P was common in both, they will cancel. And so this is really just equal to, and the halves will also cancel. So PV multiplied by PQ, PV, we'll see that as a ratio of 2, multiplied by PQ, that's going to be a ratio of 1. So we're going to just say these cancel, and we're saying we have PV as a ratio of 2. If you like, you can call it 2B, and you will just see how it would still cancel at the end of the day, okay? So if it was 2B and we said multiply by PQ, which we saw was just 1, or we could just say A, and then this goes over PT times PS. So PT is that entire length, which you can see is 2B plus B. So that's 3B. So 3 as a ratio. So we could say 3B multiplied by, and PS is this entire length, which will be the A plus the A plus the A, which is 3A. It's a ratio of 3. Okay, so looking at it like this, you see that the letters would still cancel because these are just ratios. Okay, so when they cancel, we really just have 2 times 1, which is just 2, and then 3 times 3, which is 9. So that is 2 over 9. The ratio of these areas just equal 2 over 9. And that is our answer. Question 9.2 says, in the diagram below, B, C, and D are points on the circle. And then we have that ADC is a straight line. AB is a tangent to the circle at B. Okay, so that's going to be an important point. This is a tangent to the circle at B. And the first question, 9.2.1, says we need to prove, given reasons, that triangle CBA is similar to triangle BDA. Okay, let's highlight those triangles first. So CBA, from C to B to A, is this triangle. And then BDA is BDA. Okay, so we can already see from this that they are sharing an angle, angle A. So we already have 1 in the box. We have 1 equal in both triangles. And then the only other thing to use is this tangent they gave us. So let's use that. The angle between the tangent and the chord is equal to the angle supported by that same chord. So there we go. In the red triangle, we have angle B1 being equal to angle C. And then by default, the other 2 angles will be equal. Okay, so let's go ahead and name our triangles first. So we'll just tell them in triangle CBA and triangle BDA, then we have angle A being equal to angle A, and this is because this is a shared angle. So it's not something we have to look for, it's just already shared. And now we have that, and we can tell them that angle B1 is equal to angle C. Okay, so we can tell them angle C equals angle B1, just following the same order of putting the blues first. So angle C equals angle B1, And we can tell them that that is because of the tan chord theorem. Okay, so because the tan chord theorem here is true, those are equal. Okay, so because of the tan chord theorem, and then by default, because these two are equal, the third angle in each triangle will have to be equal. So that means that angle D1 is therefore equal to angle B1 plus B2, okay, because that is the entire angle, that third angle of the blue triangle. Okay, so it means that we can just call this angle ABC. So therefore, angle ABC is equal to angle D1. And you can either say third angle in a triangle or the sum of angles in a triangle. Okay, so now that we have that, we can finally just conclude that therefore this means that triangle CBA is indeed similar to triangle BDA because we have 3 sets of equal angles in each triangle. And that is our answer. Moving on to the next question. Question 9.2.2 says we need to prove that AD times DC equals AB squared minus AD squared. Okay, so let's just see how these relate to the sides we have in our triangles. Okay, now because we already proved that these triangles were similar, we can just use their proportions because they still refer to the sides that we have. So let's use these proportions and just see how we can, instead of looking at the diagram, let's just see how we can actually form this using these proportions. Okay, so since we know that these two triangles are similar, how can we form this? So it includes AD, DC, AB squared, and AD squared. Let's see what we have here. Well, do we have AD? Yes, we do. Okay, so this side over here, if you take these two, the second and the third letter, and you also have to take the second and the third letter here. So that would form BA, or we can just call it AB, over, and then DA, or we could just call that AD, is equal to, and let's just see, which other side do we have? DC is not here, so we'll hold off on that so long, but we do have another AB. Okay, so it's probably where the squared is coming from. So we have AB, and then we would have to take that with AC. So we can just tell them AC over AB. Okay, and let's see where this goes and see whether we can actually reach this or not. Okay, so when we cross multiply, we're going to get, and of course when using these proportions, we'll tell them this is because we had similar triangles. Okay, and you can just state the triangles that were similar. That was triangle CBA was similar to triangle BDA. Okay, so now let's cross multiply here. So that's AB times AB, which gives us AB squared. And then we have AD times AC. So now looking at what we have in our question compared to what we have here, we've got AB squared, we have an AD, just one of it. And then we don't have DC, but we do have AC. So now our focus can be on AC. AC has to be some sort of line that help to somehow include DC. Okay, so let's go ahead and look in our diagram and see what is AC. Okay, so AC is this entire length. And do you see that AC is made up of AD plus DC? That actually makes sense. So let's actually note that down. We'll say that AC, but we know that AC is equal to AD plus DC. So in place of AC here, we're going to substitute this. So long, our equation is now AB squared is equal to AD multiplied by, now it has two terms, so we'll open up a bracket, and so we're saying AD plus DC. Okay, and then we can just multiply in. Okay, so you see where that AD squared came from. So it means that AB squared is equal to, so this distributes in and becomes an AD squared. That distributes in and becomes DC. I just want to put it in their order. Okay, so it's AD times DC. Okay, AD times DC. And now all they did was made this the subject. They just made AD times DC the subject. So we'll leave it here. So AD times DC is equal to, and transpose the AD squared. So we have AB squared minus AD squared. And there we go. That's what they have. Okay, so just writing it like that. Putting this on the left and this on the right. And that is our answer. And that is how we prove that. Okay, so that is it for question 9. Okay, so that is the last question. And that is it for this paper. Hope you guys enjoyed it. Please make sure to like, share, and comment if there are any questions that you have concerning it. And I will see you guys in the future videos.